Good morning. Am I audible? Is this working? Okay, yeah, okay. Good morning, everyone. So welcome to the second day of this workshop. It's my pleasure to introduce the first speaker of today, Professor Jayakumar Radhakrishnan. So he is a faculty member at ICTS Bangalore, and he is also an adjunct professor at CSA here at IISc. He works in the area of complexity theory, randomness, and computation, quantum computation, information, and combinatorics. In 2008, he was awarded the Bhatnagar Prize, which is the India's highest honor in mathematics, science, and technology. So he's going to talk about ways of computing.
So good morning. Thank the organizers for the invitation, and also, we've had some very engaging talks yesterday. So let me restore the balance. So as the abstract said, there are two things I want to tell you about, and both of them to a lay person might appear like impossible tasks. So the first is this. So I have a Sudoku puzzle, and I claim that I have a solution for this. Okay, and I want to convince you that I have a solution, but I don't want to tell you the solution. I hope. Okay, good. So so the solution is on the back, and I checked that there is nobody looking at it. Okay, so that's the first thing. And can this be done? Is there some way I can convince you that I know the solution without telling you the solution? Okay. So the second thing is, so we have a device like a firecracker, and if it works properly, then when you operate it, it explodes. But if it doesn't work properly, it's just a dud, nothing happens. Now, I have this whole large number of firecrackers, and I want to check which of them are duds. And I still want to retain the collection because, I want a celebration in the evening. So how do I test a firebomb, a cracker, without exploding it and still know that it's not a dud? Now, if the only thing that differentiates a dud from a cracker, a live cracker, is whether it explodes or not, how do you test it without exploding it? And it turns out that if you believe certain things about quantum mechanics, then this is indeed possible. Okay, so we will see, how this can be done. Good. So, part A, Sudoku. So here is this Sudoku puzzle, and you suspect that this Sudoku puzzle is not solvable. Okay. Now, I have a solution, and I want to convince you that it can be solved. And turns out that if you allow randomness, sorry, I don't know why I'm pointing there. So if you allow randomness and with some small probability of error, then such a method is possible for us. Okay. So here's the method. Okay, so let's first understand. Sorry, what am I doing wrong? Yeah. So let us understand what it means for a Sudoku to be solved. In each of the empty cells, I have to fill up digits in the range 1 to 9. And there are 3 constraints. Each row must have all 9 letters, yeah? All 9 digits in each row. Each column must have all 9 digits. Yeah? And furthermore, each of these 3 cross 3 squares must have all 9 digits. So these are the 3 constraints. Okay. How do I convince you that the solution I have satisfies these 3 constraints? Okay. So here is what you do. You tell me to write down the solution at the back. What does it mean? The value that I intend to put in this cell, I write behind it. Okay, so there's a little bit of a mirror image here, but doesn't matter. So if I want to put 4 here, I should write 4 here. Okay, good. And presumably, I have filled all this up, and wherever you put 5, I should put 5. I should not change the game. Yeah. So I have this solution, and I claim that I have this solution, and you suspect I'm bluffing. Okay. So here is the protocol. Okay, so this part is done. I have written the solution at the back. Now, since you think that I'm bluffing, it's either this constraint that is failing, that is in one of the rows I'm cheating, or one of the columns I'm cheating, or in one of the squares I'm cheating. Okay, so one of these 3 constraints is wrong, if you believe that I'm bluffing. So here is what you do. You choose one of the 3 constraints at random. You guess which one is wrong for the solution I have written at the back. Is that okay? Yeah. So once you do that, suppose you decided that, show me the rows. Yeah. Now, what I'll do is I'll cut this Sudoku along the rows. Yeah. So I'll get little strips. Yeah. I won't give you the strips. I'll cut them further into little cells. So first, I cut the first strip, keep it here. Second strip, keep it here. Third strip, and 9th strip somewhere else. Each of them, I will chop up into cells. How many cells? 9 cells. So the total number of little pieces I have is 81 in 9 piles. Each pile has 9 slips. These slips I completely jumble up and hand it over to you. The next strip I jumble up completely. I again hand it over to you. It can be to the same person, to a different person. And I just ask you to check that I have not cheated. Now, what does that mean? That I have not cheated. What you should verify when you receive what I claim was the first strip, that is pieces of the first strip, you should check that wherever there is 9 written on this side, there is also a 9 on the other side. Okay? And you should check that all 9 numbers appear in that pile. And all 9 numbers should appear in the second pile, and all 9 digits should appear in each of the piles. And in each pile, whenever a letter has been, a digit has been mentioned on this side, on the other side, you just flip over and check it is the same digit. And once you have seen this, you have to be convinced that at least I didn't cheat on the rows. Each of my rows had all 9 digits, yeah? But it's possible that I had actually cheated on the columns, yeah? But you can ask me, okay, let's play it again, yeah? Now, you again toss a coin, a 3-way coin, and decide this time to either ask for the rows or the columns or one of the squares. if you do it systematically, that is the first time you will ask for rows, the second time for columns, and third time for the squares, then I will cheat. Because there is no reason why I should put the same solution at the back of this and this. But you are guessing randomly. So when I pick this up and hold it in front of you, I don't know which question I'm going to ask. And if this was not the correct solution, then you will catch me with probability 1 in 3. Okay? Yeah, so that is what. So let's just go over what is written here. I hope I said what is written here. Yeah? That is, I cut up the paper in front of you, and you verify that each of the 9 piles of paper have all the 9 digits as required. By as required, I meant whatever appears in the front should appear at the back on those slips. Yeah. And if I am honest, then I have no problems playing this game with you. If I'm really honest and I have put up the solution, each time, all the people who are trying to verify will succeed, will have no problems. If I am cheating, then the chances that I will succeed is at most 2/3. Yeah. And suppose you say, oh, you know, I think he's bluffing, but he got away this time. You play this game 100 times. And each time, suppose I'm able to answer your question satisfactorily, then, you know, any reasonable person would say, I must have had a solution. Because if I didn't have a solution to succeed each of the times, is very unlikely. Okay. So this is how I convince you. Oh, by the way, what did you learn? Yeah, so let's go over this. So it could be that, you know, you have this Sudoku, and it's considered a very hard Sudoku. I looked it up on the net. And I solved this, and I you know, interacted with you in this manner. Now you're convinced that you have the solution. Yeah. You go home and tell your mother, Mother, here's a Sudoku, and it can be solved. I mean, given her past experience, she knows you're bluffing. So she says, convince me. He says, oh, I'll convince you using this protocol. Yeah. She says, sure, yeah, if you can do this 100 times, I'm going to be ready. And then you start off, of course, and then she says, okay, cut the first thing, and you cut. And now you're stuck. Yeah. All that you have are those 10 piles of little slips of paper. What do you do with them? Yeah. So this is a proof. Yeah, I'm not saying it very well. So I gave you those 10 piles of paper, and maybe if I did it 100 times, 9 piles of paper, and if I did it 100 times, there are these 90 little piles of slips, and each of them you had verified and you are completely convinced. But when you go and you say, look, Mother, I have a pile with 10 slips. And you know, wherever 2 appears on the other side too. Mother says, what? I could have made this pile myself. I don't need your help. Is this clear? The pile, the content of the first pile, you already know what it is going to be. It is going to have all 9 letters, and wherever 2 appears, 2 will appear on the other side. Wherever 5 appears, 5 will appear on the other side. So it is one of those proofs which you sort of know. But the fact that that proof was extracted by cutting strips of paper and chopping them up, that is what convinces you. Yeah. So I'll let you think about what makes this a proof, and what I just said, that is, even though you interacted with me 100 times, you are not in any position to go and take this proof and convince someone else. That is what makes it zero knowledge. this proof reveals to you only that there is a solution and I have it, okay? But doesn't in any way allow you to convince anybody else that this Sudoku has a solution. Okay. Is this all right? So actually I made this up, so so we can do a little demo and you can, so I need scissors. Actually, I wasn't sure about the security, so I kind of smuggled it in. So okay, good. I hope I can get out. Okay, so you tell me, believe me, suppose I was bluffing. So either the row constraints are messed up, the column constraints are messed up, or one of these squares is messed up. Squares. Okay. So let me then, So I should actually do it in front of you. Yeah. People are taking photographs and it's messing up. They just want to show off to their mothers. Okay, so I chopped off this square, and I'm now going to give you it's okay. So there should be a total of 9 little slips of paper here. So you can, So here is, I mean, you are the chair, you are sympathetic, somebody who trusts me less. Okay. No, so let me just say, what is he going to check? So he got this little square. He must check that he has all 1 to 9 there. And he must check that wherever 2 appears, I did not cheat and put 4 on the other side, okay, or some other number. So each of these which has a letter on one side should have the same letter on the other side, and the others should have a blank on one side and maybe some other thing, but they should together have all 9 letters. So can you just check that for me? Really? I don't know how that happened. Maybe the glue got off. This is terrible. No, maybe do you have 10, 11 paces instead of? No, but I shouldn't. That it may be that I stuck 2 things, and while cutting one. Sorry? Which it should. It was a 3 behind a 3, and that 3 got detached. The glue was not good enough. Trust me. Okay. But so let me try this one. Okay, so let's see. I'll do it here. I mean, for an audience of this sophistication, I really don't need to do this, but good. So that is the problem. I think some 2 of them got detached or something. That's why. So I hope. So if the front and the back don't get detached, then okay. So while they check, let's just go over some philosophical aspects. So we are all taught proofs in schools, and what is So is it okay? This one is fine. Yeah, so if I had done it right, it would have worked and things like that. Okay, whatever, doesn't matter. But you get the idea. If I'm bluffing, there is 1/3 probability of catching me. And if I manage to go through 100 rounds of this and you are never able to catch me, then you have to trust, or you have to believe, start believing that I do have a solution. Okay, that's the main thing. All the rest is gimmicks. Yeah. Okay. So now, question? If you, so yeah, so you can use cryptography to substitute for the randomness. Yeah. Otherwise, if there was, but another way, about convincing you, of course, I don't need the randomness. I can show you the solution. Yeah. But if it has to be zero knowledge, that is, yeah, then you cannot eliminate the randomness because otherwise, when your mother does the protocol with you, if she's not using randomness, then her behavior will be exactly the same behavior as you, and she ought to be convinced as much as you were convinced now. So if there is any hope at all, if there has to be any hope at all of convincing you without conveying the solution, randomness must be involved, or some substitute for randomness through cryptography, through trapdoor functions, something like that. What is randomness? Unpredictability. Yeah. If there was some way in which I could look deep into your eyes and mesmerize you into choosing one each time out of the 3 choices, then I can rig up the solution. Yeah. The fact that I don't have control over your randomness is what makes this work. Okay. So what makes this work needs a little bit of thought. All that cannot be done in this short while, but I would like you to think about it. Yeah. So what does a classical proof system do, and what is a proof? Yeah. So there are statements and there are justifications, claimed justifications. And when is a justification valid for the statement? This depends on a verifier. Okay. Somebody says that I will accept your proof if it follows this rules. Yeah. So that is the job of a verifier. What does a verifier do? When presented a statement and a justification, he says, okay, I'm happy with this justification. No, I'm not happy with this justification because you got from this step to this step. I don't know how. It doesn't follow the rules of logic. Okay. So now, whenever you have a proof system for some problem, you demand 2 things: that all true statements must have proofs. Okay. And this, in your computer science courses or in your logic courses, goes by the name completeness. Every proof, every true statement must have a proof. On the other hand, your verifier should not be so lazy that he accepts everything. Whatever statement you give and whatever proof you get, it's okay. He should be discerning. That is, if the statement is false, if this statement is false, no matter what justification you try to provide for it, the verifier should not accept. This is what a classical proof system does. What has happened now? If the statement is true, which statement? That this Sudoku has a solution, not this Sudoku, any other Sudoku. If it has a solution, then there is a way in which I, the prover, can interact with you and convince you over 100 rounds without fail. That means my probability of success is if the statement is true, then with probability 1, I can convince you. And if the statement is false, that is, my claim that this Sudoku has a solution is false, then what is the probability that you will accept over these 100 rounds? Yeah. In classical proof systems, this number used to be 0. In this randomized interactive proof system, we are ready to live with, instead of 0, a very, very small number. Okay. Yeah. Now, what physical assumptions did I make which makes this proof go through? Yeah. Perhaps that after you committed, after you said, show me the squares, I was not able to quickly change the numbers at the back. Yeah. So there was a certain commitment from my side So that there is some physical thing, that is, there is no way this prover could have, after listening to me, looked at this and using the powers of his eyes, changed the numbers. If I could have, then this is not a valid proof. The fact that this is a valid proof depends on some assumptions about how paper and pen and ink, gravity, glue behave. Okay. All right. So this is all I wanted to say about how you convince somebody that, that a Sudoku puzzle has a solution without telling them the solution. But you should convince yourself that the interaction gave you no information. The results of the interaction you could have generated yourself, if you only trusted me. Okay, so now we move on to the second impossible thing. Non-destructive testing. And sorry, I have 15 minutes. My clock has stopped. So non-destructive, can we find out if the device we have is a dud or not without destroying it? Okay, good. So again, I mean, some of you know, have quantum mechanics, and maybe many of you don't, but just play along. Don't switch off. I'm trying to say things the way I first tried to understand them, okay? And I'm hoping that it will be useful for you too, okay? So here is an experiment, and it's a physics experiment. We'll come to our tester later. So here is what happens. So I don't know if it is still done, but in school, when I had to report on a physics experiment, I had to write the apparatus on top, and then results, whatever, experiment, observation, conclusion. So let us start with apparatus. I won't. So what does this look like here? So there are these beam splitters, this and this. These are beam splitters, and there is a mirror here and a mirror here, and there are these two detectors, and one photon is passed through this system. Now what happens to that photon? That photon either splits this way, either goes up or goes down. It's like the juggling ball. You throw the ball and it deflects either this way or that way. No difference for the moment. So the photon could either go up or go right. And then of this mirror, if it had gone up, it would bounce and go in this direction. And if it goes this direction. 1 second, is it possible for me to? I'll change the color. So, that's right. And when it hits this beam splitter, that photon can also deflect this way or this way. Now, when this experiment is performed in a lab with a single photon, so it is possible for us nowadays to really calibrate our devices so that they emit one photon and then photon. The word beam is because what a laser emits is a whole bunch of photons, and each of those photons goes through this process and emerges at the end somewhere. Okay, but nowadays you can, let us say, do things one photon at a time. So when this photon is sent through this, true, it will either emerge here or emerge here. Okay, just like our ball. The ball will deflect, bounce, deflect, and reach one of the detectors. Now, suppose I put a little screen here. You understand where I'm putting a screen? Immediately after the beam splitter. And I send one photon. I always observe that the photon is either coming out here or coming out here. That is, on the screen, an impression is made there or here, but never both impressions. So it looks like a photon is an object. It's not some fuzzy thing which is passing through. it either hits on top or hits at the bottom. Okay, never both. Yeah, so I start believing that photon is like a pebble or a ball. Yeah, and if I block this, yeah, so I send a photon, I block this, maybe none of the detectors fires. Oh, then I say, oh, maybe the photon was trying to go this way and it got blocked. If I block this, yeah, it will be detected in one of these detectors. But when we observe the statistics, it turns out that when you block one of the paths, it will appear, it can appear with equal probability on either of these detectors. Okay, and if I block this path, also it can appear on one of those detectors with equal probability. No difference from a ball. You send a ball, it deflects. Whenever it hits a deflector, we don't know. It sometimes goes this way, sometimes goes this way. So what is so strange about photons? It turns out that if the first path is blocked, then the photon is equally likely to appear at either detector. If the second path is blocked, what do I mean by that? If I block this, equally likely. If I block this, equally likely. If I leave both of them around, then somehow the photon always shows up in one of the detectors, not both. Yeah. If I leave this, if you send the photon this way, it comes out this way. If you had sent the photon this way, it would come out this way. Yeah. But if you block one of them, then it emerges at. Now you see, so far we were saying, okay, this is some probabilistic thing. Nothing new happens in photons. Something spooky is happening, and I would like to spell out what is so spooky about this. In probability, suppose one outcome can then lead to two different outcomes. Yeah. So, I mean, if it is sunny, then D gate may be open or closed with equal probability. Yeah. If it is raining, then the D gate will be open with probability 2/3, closed with probability 1/3, because that is how the guard there behaves. Okay. Yeah. Beam splitter. Okay. Yeah. Now, suppose it is sunny with probability 90% and what did I say? Cloudy with probability 10%. And then I ask, what is the probability that the gate is open? Can you say, oh, if both possibilities are there, then there is no chance that the gate is open? No, if both outcomes have certain probability of some outcome happening, then if I run the system with a balance with some weighted average of these two, that outcome cannot suddenly vanish. Yeah, it will still have some probability. But no, when photons are played around with this, when this is blocked, that it is a sunny day. On sunny days, gate can be open or closed. On cloudy days, the gate can be opened or closed. But if I let the system run without telling you whether it is sunny or cloudy and ask you to predict, it seems the gate will always be closed. Yeah. Now, you cannot argue. This is what is observed in the labs. So let us just, so now I'll, yeah, question. Which of those two it will come out? Sorry, if no, we know which one it will come out. Okay, yeah. Sorry, if both of them are open, if originally the photon was approaching the system from the, yeah, it was moving rightwards, then it will come out upwards, let us say. And if it was moving upwards initially, then it will move emerge rightwards at the end. Is this clear? I mean, this is what happens. I mean, yeah. Now, good. So let us, is this okay? Yeah, Okay, so yeah, I should have drawn this on this bigger picture, but now it's gone, doesn't matter. I would like you to, yeah, so this is math, yeah. So let's see how the math works for balls, yeah. How would we say if we had to go and tell somebody in the 10th standard or 11th standard how one should think about this process classical probability with balls? We will say, one second, let me just, yes. No, let us say that the photon is approaching from the left. The question was, does it approach left or right with equal probability? No, nothing like that. My photon is going this way. The initial conditions are fixed. It is going always rightwards into this beam splitter. Okay. If no obstructions were placed here, it would always appear here. But if either obstruction is placed, it seems to have equal probability of appearing it, or appearing on this, or not appearing at all. That's a different matter. No. At this point, when I place a screen here, when I send this photon like this, it seems to come here or here with equal probability. So the splitter is a splitter in probabilities. Yeah? Just like when I send a ball to this deflector, it seems to deflect here or here with equal probability. No problem about that. Yeah? All splitters seem to behave like this. But when I put them together with mirrors, spooky behavior starts. Yeah, and people have imagined that these could be light years away, and still it will have this behavior. Yeah, the photon, well, photon remembering which splitter it came through is fine. That doesn't explain this. Whether the other channel was open or not, the photon passed this way. Yeah, I came to IISc via, I don't know, Bell Circle. Yeah, and I get to know whether there is a block in Yashwantpur. Because because always it passes through one of them. But when I leave both of them around, it always, yeah. So if there was a block here, its behavior here is 50%, 50%. If there is no block, 100% on one side. Yeah. Okay. Now let's go through the math. Yeah, I'm a little slow in time, but let's do it. Yeah. Photons travel at a speed of light. Yeah, okay, good. Yeah. So, you see, how would we, 5 minutes. Yeah. So, how would we do this in classical? We would say a right traveling ball, after it meets the first beam splitter, is equally likely to go up or go right. Yeah? And if it is traveling up into a beam splitter, it is equally likely to go up or right. Yeah, so don't be intimidated by this notation. I'm just saying if you feed an up into a beam splitter, it comes out up or right with equal probability. The two halves there tell you the probability. Yeah? And let us just evolve. The first beam splitter sends the right moving ball to up or right. The mirror turns an up moving ball to a right moving ball to an up moving ball, and then this final splitter moves this right moving ball into an up or a right with equal probability, and an up moving ball to up or right with equal probability, and if you add all this up, you get up or right with equal probability. Yeah. This is how we would have done a calculation for usual probability if we were forced to use this notation. Okay? But nothing new has happened. Yeah? How do physicists explain what is happening when the same thing happens? One thing is they work with amplitudes which are square roots of the probabilities. Don't worry about that. Yeah? That is not what changes things. When you feed a right moving photon into a beam splitter, it comes out up or right with equal amplitude. When you feed an up moving photon into this beam splitter, it comes out up or right with equal amplitude, equal probability. But they say that actually there is a negative sign in front of this amplitude. Now in probabilities, we are not used to have negative probabilities. But apparently nature holds on its little slips these things called phases. Okay? We cannot see them, but they manifest themselves when we perform experiments. Okay, so this is how physicists are today able to explain this. If we put a screen here, it will be probability half, it will be probability half. But before you observed it, actually the two were not in the same state. In one case, it was 1 over square root 2, 1 over square root 2. In the other case, it was 1 over square root 2 minus 1 over square root 2. Okay? Then let us do the math exactly as we did before. And the trouble is that this plus and this minus, there is no difference between this picture and the other picture. 2's have been turned into square root 2's. Yeah? And there is a cancellation, and all that is left is up. Yeah? So somehow, this is how they are able to set up the math to make the experiments justified. I mean, a famous physicist said you shouldn't trust your experiments unless they are confirmed by theory. Yeah. Okay. Yeah. So now, finally, I might go 2 minutes. Yeah. Let's see what we can do. Yeah, I was planning to do a demonstration, but I wasn't sure I'll be allowed to bring in a bomb. So, sorry? No, half the time. So the conclusion will be that I have a whole collection of bombs. I pass them through this experiment. Half the time, let's see what happens. So it is all the same, there is going to be this bomb that is blocking this path. And we know that when things block this path, strange things start happening to photons. Yeah. So what happens is that if the firecracker is a dud, if the firecracker is a dud, the photon always comes up. I mean, it goes in this way and comes out this way. Yeah. Otherwise, if there is something happening on one of the channels in Yashwantpur, then the photon is equally likely to come out here or there. So if the photon comes out here, then I know it's not a dud. Because if it was a dud, it would always come up on top. But maybe whenever it comes here, and this is the surprising part. Sorry, what? Okay, sorry. So this should have been a D1. Yeah. So when the photon does come here, I know that it is not a dud. But actually, the way the calculation will turn out, half the time, the cracker hasn't even exploded. So with probability half, I will see the photon here. And on half of those cases, when I look at my firecracker, it stays unexploded. So I know it is not a dud without exploding. Okay. And how does the math work out? Yeah, so the last 1 minute or so. Yeah. So what is a dud? If a photon is moving right and the cracker is in the off state, it stays in the off state. If the photon is moving up and the cracker is in the off state, it stays in off state because it's a dud. It doesn't change its state based on where the photon is. But if it's a live cracker, a cracker with the ability to explode, then if the photon passes near it, if it is a rightward moving photon at this point, then it will explode. But if it is an upward moving photon is far away from the cracker, nothing happens. So this is how you model a live cracker and a dud. Dud does nothing. A live cracker changes its state provided the photon is near it. Now let us do the same mathematics as before. So now we have two objects whose states we are tracking. One is the photon itself and the other is the cracker. That's why there are two objects separated by comma, and you just evolve it as you did before for the classical or for the randomized. And if you do the final calculation, you have these four outcomes. Either the photon is upward moving and the cracker has gone off. Yeah, too bad. You wasted the cracker. Or it is rightward moving and the cracker has gone off, wasted the cracker. It has moved upwards and you saw that the cracker has not gone off. But this is what you are likely to see even for duds. So you cannot make any conclusion in this case. But with amplitude 1/2, it could be rightward moving and the cracker hasn't gone off. And in this case, you can conclude, because this rightward moving wouldn't have happened for duds. So it is not a dud, and the cracker hasn't gone off. Hasn't exploded off on, okay. So this half translates to 1/4 because we square amplitudes to get probabilities. Okay. Now, sorry, I'm probably gone over time, but I wanted to say something about quantum computing and how all this happened, but let me just summarize. What did I tell you? I showed you a zero knowledge proof of Sudoku, and I showed you this bomb tester. This used the power of randomness and maybe some other assumptions, which I would like you to think about, and this used quantum magic. Okay, and thank you. Yes, sorry to go over time. Yeah, questions? Yeah.
Chop them up, how much effort is it to reconstruct the proof?
Oh, you will know what is the first row, what is the second row, everything.
But if you shuffle the slips, you still have
I mean, most probably you will see where I have the same letter on both sides, 2 and 2, so you will know that that is the first row because...
Oh, because the back is...
yeah, I mean, 2, 5, 1 and 9 are the slips which have the same letters on both sides. There is no other row with 2, 5, 1, 9. Yeah. Question?
I was trying to figure out what knowledge is gained by the fact that there is some printed information, right? It's not completely information free.
Yeah.
Can you comment on that a little bit? It seems like it's not, there might be some knowledge being leaked there. The fact that I completely destroy the ordering by shuffling it, turn it into a set. I turned from a vector into a set.
From a sequence into a set. Yeah, I turned a sequence into a set.
But I know something about the position on the board, and I guess that doesn't affect anything at all, right?
And the way to argue this is the final distribution of the set that you got. Could you have reconstructed it without my help?
Right. Yes. Yeah.
In which case, so when do I transmit something to you? When I say something to you which you couldn't have constructed yourself. The content of the first strip. Yeah, so this protocol can be implemented using cryptography by using hashing and things like that, where there was a commitment involved. And commitment, you might have heard, those of you who work in cryptography. So whatever protocols one uses in cryptography for commitment, you could continue to use that. Yeah. I'm sorry for going over time.
Then let us thank Professor Jaikumar.
Thank you.
Okay, so now we'll start another exciting session. It's a mini session. So till now you have heard mainly, am I audible? Yeah, till now you have mainly heard professors and pioneers, but now we'll hear rising stars in our department, our students. So there will be 4 student presentations. The first one is by Debojyoti Kaur. So Debojyoti is a PhD student in CSA department at IISc. He did his BTech from IIT Kharagpur. His academic record is stellar. He was IIT JEE topper from Eastern Zone. He had All India rank 12 in KVPY. I'm trying to remember all these ranks, and JST All India rank 2. And he also topped IIT Kharagpur BTech and got silver medal there. And then he joined our department and he received a PMRF direct entry fellowship, which he declined because he also got Google PhD fellowship. And those of you who don't know about Google PhD, it's very competitive. All over the world, only 50 students gets the scholarship. And yeah, Debojyoti is doing very well in his research. Particularly, he is interested in approximation algorithms, computational geometry. Oh, I forgot. Oh, before we start, I forgot. We should have. Yeah, so he is working on approximation algorithm, computational geometry, and game theory. And this particular talk, he will talk about how to play games theoretically.
Okay. Is the mic audible? Yeah, okay. Okay, so this is sort of going to be an introductory talk on game theory, and I want it to be as interactive as possible. Okay. So let's begin with how do we model a game in computer science? Is it working? Ah, okay. So what do we mean by a game? A game is basically a scenario where there are multiple players and each player has a set of strategies to choose from. Okay? And the outcome of the game depends on the actions that each of these individual players take. Fine? And each player derives an utility from this outcome. Okay? And now this definition is a very simplistic definition, and it's not some esoteric mathematical thing, right? Pretty much an umpteen number of things in day-to-day life can be modeled by this. So let's take a very common example of this rock paper scissors game, which we have all played at some point of time. So this is a two-player game, and each of the two players has three strategies to choose from. Either you choose rock, paper, or scissors. Okay? Now, if both of you play rock, then your strategies cancel each other, and both of you receive an utility of 0. If one of you play rock and your partner plays paper, then the guy playing paper wins, and so he receives an utility of 1, and you receive an utility of -1. Similarly, if you play rock and your partner plays scissor, you win the game, and you receive an utility of 1, and your partner receives an utility of -1. So this is a very simplistic way to model games. Okay. Now let's look at some common assumptions that we make while studying game theory. So the first assumption is called rationality. So what this says is that I am participating in the game, and my only objective is to maximize my own utility. So I am as selfish as I can be. That's my only objective. I don't care about anyone else. Okay? The second assumption is called intelligence. That is, I am capable enough to make any level of reasoning. Okay? That is, we all are intelligent players here. And the third and the most interesting assumption is called common knowledge. So what this says is that an information I is said to be common knowledge if, firstly, everyone should know this information, right? Next, the fact that everyone knows this information should also be known to everyone. Okay? Again, the fact that everyone knows this information should also be known to everyone, and this will continue till infinity. Okay? So this might seem a bit weird. I mean, this is fine, but so how does it matter? So let's look at an example to demonstrate the consequence of this assumption. So consider this simple example. So let's say there is an island where there are 50 red ants and 50 black ants. Okay? And the red ants believe that they are cursed. But the catch is that no one knows his own color. So if I am a red guy, I will be seeing 49 other red guys in front of me and 50 other black guys. And if I am a black guy, I will be seeing 50 red guys and 49 black guys in front of me. But I don't know my own color. Okay? This is the scenario. And if any ant comes to know that it is red, it is going to publicly commit suicide. Okay? And there is no way of communication among the ants. They don't communicate with each other. Okay? So everything is going peacefully. But now suddenly what happens? A foreigner ant visits the island and remarks, there is at least one red ant among you. Okay? So what do you think this will lead to? I mean, this seems to be a very like good for nothing remark, right? If I am a red guy, I can see 49 other red guys in front of me, and you are just telling me there is at least one. So how does it, so what do you think will happen by this? Do you see any consequence of this, anyone? Yeah, you shut up. You are an IISc student. Any of these UGs? All, sorry? Yeah, and why? I think your mic is not working. Can you just switch it on? Or yeah, yeah.
So we can induct.
Yes.
So like, let's say there were two red ends,
Yes,
and like, so after this remark,
yes,
on first day, since each red end can see other red end,
yes,
so they won't commit suicide.
yes,
So they can conclude that it's because of them that the other end hasn't
yes,
committed suicide.
exactly. So let me just explain what he said. So let's begin with the most simple example. Let's say there is just one red ant and one black ant. So what is going to happen? If I am the red guy, what I am seeing in front of myself is there is just one black ant in front of me. So if someone is coming and telling that there is at least one red ant, it must be the case that I am the red guy, and so I will commit suicide. So for if there is one red ant and one black ant, it's clear. Now let's say there are two red ants and two black ants. Okay? So if I am a red guy, I am seeing that, okay, here is one red guy in front of me and two black guys in front of me. So from this information, I have no way to decipher my own color, right? So I'm happy, I do nothing. But so on the next day, what I see is that the other red guy, which I am able to see, he is also alive. He also has not committed suicide. So now I go into introspection. I ask myself, why? Why did he not commit suicide? So if I were black, then he would have seen three black guys in front of him. And by this information, he would have committed suicide, right? But he is not. So the only possible explanation is that I must be red, right? So then, and the same chain of reasoning is also going to be done by the other red guy. And what is going to happen is that on day 2, both the red guys are going to commit suicide together. Clear? And this by induction, as he said, is going to generalize for any value of n. So if there are n red ants and n black ants, then on the nth day after this remark, all of them are going to commit suicide together. Okay? So this is the power of common knowledge. So this subtle remark leads to disastrous consequences, as you can see. Okay. Now let's look at another interesting example. So let me ask this question. Suppose there is a city and there is some road network in the city. So what does this mean? So a city consists of some important locations, some important hubs, and there are roads connecting different places in the city. Now let's say a new road is constructed between some two locations in the city. So the question is it necessary that the traffic congestion improves? Or in other words, is it possible that by the construction of this new road connecting some two places in the city, the traffic congestion in the city actually worsens? Is it possible? What do you think? Yes, okay. So let's look at a simple example. The answer is yes. So adding more roads to a road network can actually slow down the overall traffic flow. So let's look at a very simple example. So here is a road network. And let's say there are, so S and T are two important locations, and there are two paths to travel from S to T. Either you take this SAT path, or you take this SBT path. Now the roads are designed in such a way that if X be the fraction of traffic taking the upper path, the S to A to T path, then the time taken to travel from S to A will be X. Okay? Similarly, if X be the fraction of traffic taking the lower path, then the time taken to travel from B to T is also going to be X. And the roads connecting A to T and S to B are such that no matter what the amount of traffic, it takes one unit of time to travel along them. Okay? So if this is the situation, then what do you think is going to happen at equilibrium? I mean, it's clear intuitively that half of the traffic is going to take the upper path and half of the traffic is going to take the lower path, right? So the value of X is going to be 1, and therefore the time taken to go from S to T is going to be 1 plus half, that is 3/2. Correct? Now suppose a new road is constructed between the cities A to B. It's a one-way road, and it's such that it's a super highway. It takes essentially 0 time to travel from A to B. Okay? So now if you look, there are 3 possible paths to travel from S to T. Either you take this SAT path, or you take this SBT path, or now there is a third road, this SABT. Correct? So now let us try to analyze the times taken to travel from S to T along each of these 3 paths. So if X be the fraction of traffic which travels from S to A, then how much time does it take to travel along the SAT path? It's clearly X plus 1. And how much time does it take to travel along SABT? It's going to be X plus 0 plus some fraction. That may not be X, because so if X be the fraction of traffic that travels from S to A, 1 minus X travels along S to B, and there is again some division of traffic at A. So whatever it is, it's going to be X plus some fraction, right? And that is always less than or equal to X plus 1. So if you take the SAB to T path, you are going to be, the time taken to travel from S to T is not going to be more than the time taken to travel along the SAT path. Correct? Similarly, if X be the fraction of traffic traveling along the B to T path, the time taken along the SBT path is going to be 1 plus X. And the time taken along the SABT path is going to be some fraction plus 0 plus X, which is again less than or equal to 1 plus X. Correct? So then everyone is going to see that traveling along the SABT path is at least as good as taking the other 2 paths. Correct? And therefore, everyone is going to take this SABT path at equilibrium. That is, the value of X is going to be 1. So, but then what happens? What is the total time taken to reach from S to T? It's going to be 1 plus 0 plus 1, that is 2. And as you can see, the time taken to travel increased from 3 by 2 to 2. Right? And this phenomenon was actually observed in real life. So this happened in Seoul, which is the capital of South Korea. So here there was a river in Seoul, and in the 1970s, some big highway was constructed over this river, named by this, I can't pronounce it. And what happened is, the authorities observed that after the construction of this, the traffic congestion actually worsened in the city. So finally in 2005, the authorities finally demolished this highway, and instead they installed some greenery across the river. Fine? So yeah, this is one very practical example of such a thing, and this is known as Brace paradox. Okay. So lastly, I'm going to focus on one more thing, which is called envy-free cake division. So this lies in a domain of game theory, which is called fair division. So the setting is as follows, a very simple setting. So there are n friends, and there is a cake. Okay? And each of these n friends has a valuation function over this cake. So what does this mean? It just means that you all have different preferences over different parts of the cake. Some may prefer the strawberries, some may prefer blueberries, or some might prefer nothing. So mathematically thinking, you can imagine it as you have an interval, let's say the interval 0 to 1, and these valuation functions are just density functions or probability density functions over this interval. And your valuation for a particular part of the interval is just the area under your curve. Okay? So this is how you can model it mathematically. And now the goal is very simple. You need to divide the cake so that everyone is happy with his or her own share. Okay? So you need to divide this interval into n pieces and distribute these pieces among these n friends so that each is happy with his own share. That is, I should not complain that I prefer your share more than what I have received. Okay? So the first question that arises is whether such a partition always exists. That is not directly clear, right? I mean, given these arbitrary density functions, is it always possible to divide this interval so that you achieve an envy-free cake division? That is not directly clear, right? So the thing is that no matter what the density functions are, it can be shown that such a partition always exists, and the proof is not simple, it goes through some fixed point theorems. Okay, so next, so what is the next issue then? So if one of these n friends is a mathematician, he will say that, okay, you give me these valuation functions, you give me this cake, I will say, okay, there is a way to partition this cake and I'm happy. I don't care, you do whatever you want with the cake. So next comes the job of the computer scientists. So you need to actually find this envy-free partition. right? Now for small values of n, let's say when n is equal to 2, this task is not all that difficult. So it's called the simple I cut, you choose protocol. So what you do is you call the first guy and you tell him, okay, you have your own valuation function. You divide the cake into 2 equal parts according to your valuation function. So you value these 2 parts equally. Now you call the second person and you tell her, okay, here are the 2 pieces, you choose your favorite one. Okay? And then the other piece is by default given to the first guy. So this clearly achieves an envy-free cake division, right? But the trouble is, this simple protocol does not generalize for higher values of n. So the first progress in this was made in 2009 by Prokashia, who showed a lower bound of n square. So this omega n square just means it's some constant times n square. So what he showed was that you take, if you consider any protocol that outputs an envy-free cake division, it must take at least, let's say, 5 n square steps. But still, this is a lower bound. You don't still have an algorithm to actually find an envy-free cake division. So finally, in 2016, Aziz and Mackenzie gave an algorithm which requires this many number of steps. So let's say if n is equal to 5, the number of steps that their protocol would require is going to be 5 to the power, 5 to the power, and so on, this tower of 6 5s. And this is finite, but it's not a small number, as you can see. And improving this is one of the most important questions in fair division. And if you are able to improve this, you will surely be nominated for a Nobel Prize. Okay, so since I don't have time, I'll just skip through this. So here is, how many of you have watched this movie called A Beautiful Mind? It's about the life of John Nash, who is famous for this, who introduced this concept of Nash equilibrium in games. And yeah, here is a list of Nobel Prize winners in game theory. So John Nash also received the Nobel Prize in '94. Then in 2020, the Nobel Prize was awarded to Milgrom and Wilson. And yeah, this is a book written by our own faculty member who you saw yesterday on game theory. And yeah, I did not discuss what Nash equilibrium is, but it's basically a situation where nobody has any incentive to deviate from their chosen strategy. Okay, I'm just rushing through it. So I'll just end with one slide and you can interpret in whatever way you want. Okay, thank you.
Let's thank Devajyoti, and I'll request Rahul to give the memento. Okay, so our next speaker is Karnati Venkata Naga Srinivasulu, or fondly known as KVN Srinivas. KVN is our PhD student in CSA department, and he did his BTech from IIT Bombay. He scored perfect score in math in IIT JEE mains, and then he worked in Samsung Research for a year, and then he thought, okay, I like research, and he joined IISc as a project assistant, and then he joined as an MTech student. He got best MTech CSA award here, and then he joined as a PhD student, and then again he is a recipient of Google PhD fellowship, one of 5 in the world in algorithms in theory, and he is working on approximation algorithms and randomized algorithms, and in this talk he will talk about randomness in computing. So welcome, KVN.
Am I audible? Okay, so yeah, today I want to show you like how randomness can be used in. Okay, so today I want to show you how randomness can be used in computer science. Okay, so first let's look at this example of calculating pi's. We all know that pi is like almost equal to 3.14 something. but I want to calculate pi using this geometric object, and we'll use randomness to do it. So there is a circle and there is a square enclosing it. So this area of the circle is pi r square, and the area of the square will be, so the side will be 2r, so the square area will be 4r square. So we can calculate pi as 4 times the area of circle by the area of square. But now I want to calculate the area of circle and the area of square using randomness. So what's the algorithm going to be? So let's say we choose some n uniform random points in the square, okay, and some of these points fall inside the circle and some don't. So if a point falls inside the circle, then we say that it contributes to the area of the circle. Otherwise, it just like contributes to the area of the square. So my estimate of the area of circle is going to be the number of points that fall inside the circle, and the estimate of the area of square will just be n. So this is my formula going to be, and we can simulate this. I've used Python to simulate this. So with 100 points, you get an estimate of pi to be 3.04, and with 1000 points it improves to 3.112, with 10,000 it improves to 3.116, and with 1 lakh it improves to 3.14056, which is very close to the value that we know. Right, but you may wondering why all this to just calculate pi. But yeah, that's the beauty of math. We not only just solve problems, we also develop tools to solve harder problems. And one such harder problem is the scene generation problem. So here you are given a scene. So you are not given the 2D image. You have to construct the 2D image, but you are given a description of the image. So basically you are told that there is a blue wall to the left, yellow wall to the right, and so on. You are told that this sphere center is at -1, -1, -1, let's say, and radius 2. The coordinates of the cuboids are also given. And there is a light source at the top of the ceiling, that is also given. And you have to construct this 2D image. By that, I mean that you should also construct the shading on the sphere, the shadows, and so on. Right, so as of now, it feels like randomness has nothing to do with this example. But we'll see how to do it. So first, we note that whatever we are seeing, it's because of the light source at the top of the ceiling, right? So we see how the light rays interact. Okay, so we are given positions of the objects. The material properties are given, whether they are reflecting or not. The light source intensity is given. So now we look at like how light interacts with the objects. So let's say I shoot a ray from the light source onto an object. So what happens? So the incident ray, it creates a infinite number of reflected rays through that solid angle omega. If the surface is like perfectly reflecting, then it will create only one reflected ray, but otherwise it will create an infinite number of reflected rays. So now to construct the scene, we want to study these light rays, but they are like infinite in number. So yeah, what do we do? So we basically want to study the infinite light rays in the solid angle. But it's not like mathematically possible. So any input from the audience? Right, so that's what we are going to do. So we randomly sample a bunch of rays, let's say 100 rays in that solid angle uniformly randomly, and we'll see how those light rays interact with other objects. So maybe the top 3 light rays, they escape the scene, let's say, but the top 2 light rays interact with this object. We then recursively compute like how these light rays, how one of these light rays interacts with the other object. So again, the reflected light rays will be in the solid angle, but again we sample a bunch of light rays, and we keep doing this until the light rays reach the camera. And for every pixel, there will be some intensity or some color that it receives. We color that pixel with that color. Okay, so that's how this is done. And this technique is known as path tracing, and it's used in CGI movies, etc. So for example, this is one example of this path tracing. With on the left, you can see with fewer number of samples, you get that image. And as the number of samples increase, you get a clearer image. Okay, and so this movie, Monster House, this is the first fully path trace movie. So path tracing was used completely to render this movie. So it's on Netflix. And nowadays, so path tracing generally takes a lot of time because at every intersection point we have to simulate like 100 rays. So it was originally limited to CGI and movies and not like real time applications. But nowadays with computing power, GPU power, we can use path tracing for games also. And these are two examples, Minecraft and Quake 2. Okay, so I would like to show some other examples in computer science. There are several other examples where randomness is used, but I would like to show three. The first problem is you want to test whether a given number is prime or not. Okay, so let's say 25573. So whether this prime number is prime or not, you want to test it, and you want to test it in polynomial time, because if you allow for exponential time, sieve of heterogeneous and all such techniques can work. So in the deterministic algorithms regime, okay, so let's first look at the randomized algorithms regime. So the right side. So there is a simple test called Miller-Rabin test, and that was designed in 1980. And it's a very simple test. It gives you with high probability whether whether a number is prime or not. But designing a deterministic algorithm for this problem turned out to be a very hard problem. And only in 2002, so there was this huge breakthrough result, AKS primality test, that gave a deterministic algorithm for testing whether a given number is prime or not. And AKS, so here AKS stands for Agarwal, Kayal and Saxena. So they were researchers at IIT Kanpur. So Manindra Agarwal was a professor, and Neeraj Kayal and Nitin Saxena were his BTech students. And this was their final year project in which they got this result. So this also won the Gödel Prize in 2006, Fulkerson Prize and so on. So this was such a, I mean, yeah, that's what it took to design a deterministic algorithm for this problem, whereas randomized algorithm is very simple. And the second problem is checking if two polynomials are of same size or not. Two polynomials are equal or not. Let's say you are given two polynomials P1 and P2. And you want to check if these two polynomials are equal or not. Okay, so maybe the first polynomial is x minus 1 whole square. Second polynomial is x square minus 2x plus 1. I mean, here it's easy to check, but in general it's a very difficult problem. And in the deterministic regime, we don't know of any algorithm as of now that you can solve in polynomial time. But in the randomized regime, so in 1979, there was this test called Schwarz-Zippel test, so which with high probability checks if two polynomials are same or not. And yeah, the last example that I have is sorting Google search results. So if you type something, then there will be millions of results, but on the first page you will get the most relevant results. So in the deterministic regime, again, there is no good algorithm, but in the randomized regime, so Larry Page gave this PageRank algorithm in 1998, which was, yeah, which used the technique of random walks to sort the Google search results, and that is being used even now. Yeah, and the list just goes on and on. So there are multiple applications in cryptography, multiple applications in graph theory, min-cut algorithms, approximating the volume of a convex body, where it can be proven that no deterministic algorithm exists, but there is a very not simple, but a randomized algorithm which achieves a very good approximation factor. Also, there is another problem called approximating the maximum number of satisfiable clauses in a Boolean formula, and so on. So yeah, there are a lot of examples, and these are some jargons that you may want to search on the internet after the talk. Yeah, that's it. Thanks.
Go to give the memento to Kavian.
Thank you. Thanks.
So our next speaker is Atashi Panda. She is also a PhD student at our Department of Computer Science and Automation. So Atashi did his BTech from BITS Pilani, and then MTech from Wisconsin-Madison. And then she has joined industry. She has worked at Oracle, Intuit, Flipkart, and then Uber, all like top shot companies. And then she realized research is her passion, and she joined us in 2019 or 20. And she's working on online learning and fairness and other interesting question in theoretical ML. And today she will talk about online learning. Oh yeah, I didn't tell. Oh, I forgot to mention she is also a Walmart PhD fellow.
Hello. Hello. Yeah. Okay, welcome to this talk on online prediction and learning. This is an introductory talk on this topic, and we'll just explore different flavors of problems that can be categorized under this. Um, uh, so some popular terminologies like exploration versus exploitation and multi-armed bandit problems, these are the things that can broadly fall under the umbrella of this topic. So we'll look at some of the basic components that make up an online learning problem. And then we'll look at one of the simplest examples, that is one-bit prediction, and some of the simple algorithms associated with the same. So let's first understand what online prediction learning is. And basically the kind of problems that fall under this is sequential decision making under uncertainty. Let's break this down and understand what each word conveys here. Sequential obviously conveys something related to time. So what this means is that once we make a decision, we cannot change it in the future. So there's this famous secretary problem. So let's say there is an interview going on for jobs, and there is a good candidate at the beginning. However, the interviewer rejects them, hoping that they'll find a better candidate later. However, if they don't find a better candidate, they can't go back and hire the candidate that they had rejected. Decision making is basically, this conveys what kind of problem we're trying to solve. For example, it could be optimization, estimation, etc. And most importantly, uncertainty conveys the problem that the learner faces with limited information or knowledge about the environment that it is learning in. So uncertainty could be uncertainty about the environment, the model, or the context or the background information that is provided to the learner. Say for example, we need to pick out of given options. However, we do not know the payoffs of these options before we make this decision. And the learner might only find about it in hindsight, or maybe not even then. So this is a kind of uncertainty in the context that is provided to the learner. Let's look at quickly look at some applications of online prediction and learning. So obviously it is widely used in AI and machine learning, like recommendation systems, etc. It's also used in forecasting, robotics, game theory, resource allocation, in general operations research, even healthcare and finance. And we'll use finance as a running example to understand what are the things that constitute an online learning problem. So let's look at the components of an online learning problem in the context of sequential investment. So obviously this is an online problem, so we do not have access to all the data in a batch form, or we do not know everything in advance, and it is provided to us in a sequential or a streaming pattern, because of which the algorithm or the learner needs to take decisions at every round. So at each round, the learner observes a context. In the context of this example, it could be the opening market prices or the history of the stock prices so far. Then the learner takes an action based on that context. In sequential investment, it is the trading decision of whether or not to buy or sell a stock. Then the learner observes the outcome, which could be the closing prices at the end of the day. And finally, the learner registers a profit or loss, which is the monetary change in the portfolio of the trader.
So obviously the learner's aim would be to keep the total loss small. However, we look at the exact goal that we aim for as we delve deeper into the simple example. So let's look at the simplest example of an online learning problem, which is 1-bit prediction. So we have a stream of bits, 0, 1 bits. We have a learner, and the learner can see only 1 bit at a time. And before the outcome is revealed to the learner needs to make a prediction, right? So we can think of it like an extremely simplified version of the previous example that we saw. Like say there is a trader and they need to decide whether or not to buy a certain stock on each day. And if at the end of the day, the bit is revealed to them, if it's 1, then they should have probably bought it because that stock ended up being profitable. If it is 0, then they should have not bought it or sold it because that stock ended up creating losses, right? So this is just we can think of it as an oversimplified version of the previous example. So let's assume that the learner first predicts 1, and then the first bit is revealed to the learner, and obviously it matches, so the loss incurred is 0. Let it also predict 1 again. Sorry, some animation is lost here. Okay, then the second bit is revealed, and this matches again, so no losses again. But now the learner say predicts 0. And of course, when the next bit is revealed to the learner, they realize that it's a mistake, it does not match. So here they incur a loss of 1. So this is a 0-1 loss problem. And if the bit that is the outcome matches with the prediction of the learner, then there is no loss. Otherwise, they incur a loss of 1. And going by the previous learner's aim that we looked at, the goal would be to minimize the total losses. But if we just think about it, a very natural but important point is obviously that the losses could be just the maximum. Because we cannot really predict the future without knowing something about the structure of the sequence of bits that is being presented to us. It's highly possible that this sequence is so complicated or in such a manner that no matter what you predict, the outcome always ends up being the opposite of that. And so you just incur the maximum loss possible, right? So yeah, we cannot predict the future without making additional assumptions. So where do we go from here? Well, one way is to have a more relaxed goal, where rather than trying to minimize the absolute loss, we want to minimize the relative loss, loss relative to some benchmark, right? So previously our aim was to keep the total loss small. Now let's update it to keep the total loss small relative to a class of predictors. So this is where the experts come in, which is the class of predictors we want to keep our loss small to, relative to those losses. Again, going back to the example of sequential investment, here the experts could be the finance gurus or people who have a very good portfolio and very profitable portfolio and study stock market and track the market very regularly, etc. Right. So now we have a bunch of experts, and these experts also make a prediction before the outcome or the bit is revealed to the learner. The problem stays the same. We have a stream of 0, 1 bits, and we have a learner. However, the difference is that now the learner has access to all the expert predictions. So what did we do? Now we have this benchmark, which is the total loss of the best of the experts. And we define regret as the relative loss of our learner or algorithm in compared to the benchmark or compared to the loss of the best of the experts. And now our new goal is to minimize this regret. Right? So how does this help? Obviously, if we have a good expert, then minimizing the regret would imply that the learner itself incurs low losses, right? But what if we have all bad experts? Well, then we should be okay with high losses, because if even the best of the best are not able to deal with such a sequence, then others have no chance. So it's okay to have high losses here. Okay, so let's look at how we can use the experts in an algorithm to make good predictions, right? Let's start with an assumption that there exists a perfect expert in the pool of experts that are given to us. So what is a perfect expert? Basically an expert who makes zero prediction errors, so they incur zero losses, right? And we have the learner who obviously has no idea who the perfect expert is, because once we know that, we will incur no losses at all. So we can reduce the problem to finding the perfect expert, right? Anyone wants to take a shot at how we can find the perfect expert? Sorry? Okay, something even simpler you can do. So what is the most simple way, like the brute force way that you can find the perfect expert? Yeah. Yes, the learner knows that there exists a perfect expert, however, they don't know who that is.
One by one try?
Yeah, that's the brute force way, right? So, but obviously, we'll incur more losses if we do that, and our aim is to reduce the losses, right? And like, there is a hint in the title itself, we can just half it. So, we just predict by majority opinion first. So, that just means that if there are, the majority of the experts predict 1, then you predict 1. If the majority experts predict 0, you predict 0, right? Then more importantly, in the next step, you discard all the experts that made a mistake. So there are no second chances here. Once you make a mistake, you're out of the experts pool, right? So what happens then? So let's say that the algorithm or the learner made a mistake. That means that at least half of the experts made a mistake just by how the algorithm runs, right? So we can get rid of at least half of them. Let's say it makes another mistake, so it goes so on and so forth until the perfect expert emerges. And once we know the perfect expert, obviously we don't make any more mistakes, right? So what did we do? We assumed that we had m experts, and there is one expert that incurs 0 losses. And that helps us to reduce this problem to finding the perfect expert. That means that the number of errors made by the halving algorithm that we just discussed is bounded by log m, where m is the total number of experts, right? Because for every error, you halve the number of experts, and so obviously you can narrow it down to 1 expert who never gets eliminated in log m time when there are m experts, right? It obviously looks like a simplistic algorithm. It is a simple algorithm. However, it turns out that this bound is actually tight in a worst case sense. What that means is that for any one-bit prediction algorithm, you can always have a sequence of 0-1 bits and expert predictions such that the number of errors made by that algorithm is at least log m, given even in the presence of a perfect expert, okay? So one thing is obviously the one unrealistic assumption that we made is the presence of a perfect expert, which is unrealistic because even if we go back to our example, even if there are finance gurus, none of them have incurred 0 losses, right? So what is a better way of looking at it is to have some best expert or best experts who may not be perfect, however, they incurred the least number of errors or losses, right? Again, the learner does not know who the best experts or expert is. We can again find the best experts by making a very minor modification to the existing halving algorithm. So you still predict by majority opinion, and you discard the experts that made a mistake, okay? So that's what happens, like they start disappearing. However, since you don't have a perfect expert, even the best of the experts are going to make mistakes. So they can also get eliminated from this pool, right? So it's possible that you're not left with any experts. So then how can anyone guess what is the minor modification you can do to just get over this problem? Okay, you can just repopulate them again, right? So let's say that the mistakes made by the best expert is c, some constant c, which is strictly greater than 0. Then we can easily show that the regret is bounded by c plus 1 log m. Is it easy to see? Because this thing will vanish, everyone will vanish at most c times. And after c mistakes, there will be at least one expert that makes no mistakes, and so they never get eliminated, right? So, and we are able to find them after that. So, yeah. Of course, this is not the end of the road, and this can be further improved by weighted majority, like you talked about, and pontificative weights, updates. And this is just the beginning of the road, but I just wanted to give motivation and like just an idea about how we go about doing these things and what regret is and stuff like that. And okay, and yeah, hopefully this is enough to encourage you guys to go and look up other things like multi-unbounded problems and UCB algorithms and all those things. Okay, thank you.
So I'll request Nildhara to give the memento. So our last student speaker is Rachana Gusai. Rachana is a PhD student at CSA department, and she did MTech from JNU, and after that she was teaching at Doon University for almost 7 years, and then she found research is her passion, and she joined us in 2022, and she is a recipient of prestigious Prime Minister's Research Fellowship or PMRF Fellowship, and she is interested in geometric algorithms and data structures. And today she will talk about how to buy oranges in high dimensions or something like that. Yeah.
Yeah. Hello. So thank you, sir, for introducing. I'm Rashna, and we will be talking about objects like spheres and cubes in higher dimensions. Okay. So we all are familiar with how these oranges are stacked in grocery stores. And interestingly, that's the optimal way of packing balls in 3D, right? And what I mean by optimal packing is that there is least amount of space between the objects. And you can see this in more intuitively in 2D. Like if you have, say, coins and you want to place them on a table in an optimal way. Yeah, so should I remove this? So if you place coins such that every coin is this not on? I don't know. Okay. Yeah. So if you place coins on a table and you want it.
Headset is better.
My God. Is it better now? Yeah. Okay. Yeah. So in 2D, say you have coins and you place them on a table in an optimal way so that the space between coins is as low as possible. So if you place them like a coin is touching just the four neighboring coins, that is not an optimal way, which is should give you a square way of packing those. Instead, the hexagonal way of packing the squares is optimal, right? So this is known in 2D and 3D. For 3D, I mean, it was conjectured sometimes in 17th century, but 400 years later, people actually showed that this indeed is the optimal way of packing. And nothing was known until 2016, like how do we optimally pack balls in higher dimensions. And in 2016, this mathematicians from Ukraine, Marina, she actually showed optimal arrangements for 8 and 24 dimensions. And for this, she received Fields Medal in 2022. Yeah, so I mean, I mean, for other dimensions, it's just completely open, like we do not know how to optimally pack hyperspheres. So we will look at some simple mind-bending tricks involving these balls in higher dimensions. So suppose I have a square and each side has length equal to 4 and it's divided into 4 quadrants. The center of this cube is at the origin, say. Now each of those quadrant has side length is equal to 2. So I can put a circle in each of those which has unit radius, right? And that's the largest circle that we can fit in each of those quadrants. Now suppose in the middle I want to place a ball, and we are interested in like what is the largest ball that I can fit in the middle, right? So how do we do this math? It's simple. Suppose r is the radius of that central ball. Then if you consider this vector, red vector, its length is equal to r plus 1, and also all these corner circles have the center coordinates is 1 or minus 1. So the norm is going to be equal to root 2, and which will give us r equal to root 2 minus 1. Okay. Interestingly, all this math also goes through to the higher dimensions. So suppose I have a ball, I can't draw the picture in higher dimensions. So still the thing is like the central ball and this red vector there, its length is going to be equal to r plus 1, and the norm of that vector will be root n, because now the coordinates are, each coordinate is 1 or minus 1, but they are any number. So the radius of the central ball is increasing with n. So it's surprising, right? So on the plane, a square with sides of length 4 can fit 4 unit discs plus one smaller disk which has radius equal to root 2 minus 1. Now what happens in 3D? The size of that central ball has increased to root 3 minus 1, but it is still smaller than the corner balls. And there are 8 corner balls now. So in n dimension, what is happening is, so you have an n dimensional cube. It can fit in 2 to the power n unit n balls in its corners, and at the center we can place a ball of radius root n minus 1. So if you do these calculations, surprisingly when the dimensions is equal to n, the central ball has radius 2, which is twice the size of the corner balls, right? And with a further increase in the dimension, the central ball is just bursting out through the sides of the cube. So this is really surprising. Yeah. Now let's take a simpler setting. Suppose I have a square again of side length 2, and I place the largest fitting disk inside it. So it has to be of radius 1. And now we are interested in what fraction of this volume of the area of the square is contained in the circle, right? So in 2 dimension it's easy, right? Area of the circle is pi, and the area of the square is 2 squares, so we get 0.79. So 79% is contained. Then in 3D, again it's easy. The volume of the ball is 4 pi over 3, and the volume of the cube is 2 cube, which gives us 52%. So more than half of the volume of the cube is contained in the ball, but you can already see the pattern. The ratio is decreasing. And how about like higher dimensions? So one thing is easy, like an n cube of side length 2 has volume equal to 2 to the power n, but the volume of the ball is given by that formula over there. So I'll get back to that formula in the next slide, but if you plug in different values of n, we get this table. So at n equal to 10, you can see that the ratio is already less than 1. So less than 1% of the volume of that of a cube in 10 dimension is contained in the ball, right? And the extraordinary thing here is that that ball still is the largest ball that can fit inside the cube. Now in 100 dimension, this ratio is very less, or of the order of 10 to the minus 70. And this means that if you select 1 trillion points at random from the interior of the cube, you have almost no chance of landing on even a single point that falls inside the ball. So the ball is there, but it's somehow disappearing, right? So let's see how to make sense of this act. So one thing is clear, that this cube is growing exponentially and this ball is shrinking incredibly. So if you look at the volume, the formula for volume of unit n ball, the numerator is exponential, is growing exponentially, but the denominator, which is a gamma function, it's a, like, think of it as a generalization of factorial. This is much, much faster than the growth is much faster than the numerator. And this is what the pattern we get. So initially the volume of the unit n ball increases. At n equal to 5, it is maximum, and then it is start decreasing. Now intuitively also we can think about it. So this unit n ball, like the unit ball that is inside the cube, it's only touching the faces of the cube. Now suppose you are in 10 dimensions. How many faces are there? Just 20 faces. Whereas the number of corners is 2 to the 10, right? 1024. So that somehow explains this phenomena, this disappearing phenomena. And now let's consider this simple example. Now I want to know that suppose I have a ball and I take a shell of the ball which has a thickness t, and I want to know, like, what volume of this n ball is contained in this thickness. Okay. So volume of shell divided by volume of the ball, and the numerator is simply, it can be computed by taking the difference of the two volumes, and by noting this simple fact that volume of a ball of radius r is r to the power n times the volume of unit ball in n dimension, we get this simple calculation. We can do it very simply, right? Now suppose the thickness is 1% of the radius. Okay, so t is say 0.01 r. So in that case we get that this ratio is 1 minus 0.99 to the power n. So for n, like roughly around 500, more than 99% of the volume is contained in this shell of thickness 1% of the radius. And this is why they say that peeling a high dimensional orange won't give you anything. Once you peel it, you are not left with anything. So with this, I'll close my talk, and thank you. Thank you, sir. I should have kept it there.
That's fine. Yeah, we can come up to yeah. So, hello there everybody. Very fantastic talk given by all of you. My question is directed towards Rachna, and it might sound very stupid, but how are we so sure that our axioms on which we have built our mathematics so far transfers like unhinged into higher dimensions? Like, how are we so sure that what mathematical basis we have right now translates into higher dimensions? That, like, so the results we got, it's quite, let's say, fascinating to imagine, like having a volume bigger than a size decreasing. So how can we say for sure that it translates into the higher dimension? Like, this is what's going to happen.
Yeah, just based on the math, and I also did some intuition about it, right? So if we in particular take that second experiment where you have a cube which has, and you put a ball which is the largest ball that you can fit inside it. So you see that ball, the way you define a ball, what is it? The set of all the points which is at a fixed distance from the center, right? And this cube has exponential number of corners. So this ball is not reaching out to the corners, it's only touching the faces. This number of faces is like growing linearly with n, whereas the number of corners is growing exponentially with n. So that somehow intuitively explains this fact. This phenomena, yeah. And still, like, many questions are open in higher dimensions. The first one itself that I showed you, in 3D we see that in everyday life, but even proving that formally, that it indeed is the optimal way of packing the balls in 3D, it took centuries. Yeah.
I have a question to you from game theory. You had said that at the 50th day, all the ends commit suicide. My question is, suppose there are two ends, right? And suppose they both are red ends. Both are red ends, and they see each other.
Yes.
I know that you are red end. I know you know that I am red end.
Yes.
So we both won't commit suicide. So don't we remember that I know that there was a red end, and hence I won't commit suicide?
Yeah, that is what is happening on the second day, right? There is no communication between us. So I am thinking from the perspective of the other guy. Right? I am seeing that, okay, I can see one red guy in front of me, but I am seeing, okay, on the first day, this guy is not committing suicide. So now I ask myself that why? Why did he not commit suicide? So I am now thinking from the perspective of that second guy. That's how. So that was the assumption called intelligence, that players are competent enough to make any level of reasoning. That was the second assumption which I had made.
Okay. So I won't remember that I had seen a red end, and okay, then
I can always see one red guy in front of me. Like I have eyes. I mean,
So with that remembrance, won't I stop committing suicide? That I had seen that red end existed, right?
Yeah.
So then I'm not that red end basically. If the red end existed.
No, why can't I can be red or black, anything. I don't know about myself. I can't see myself.
Okay.
That is the I can't see myself. There is no like mirror or any way of seeing myself. So without a mirror, how can you see yourself?
No. I assume that there was a red end.
Yeah. So the statement was that there exists a red end. So I can see one red guy in front of me. I don't know my own color.
Okay.
Yeah. No. There is at least one. At least one. Yeah, greater than equal to one. Not exactly one. Yeah.
One more. Only one, two, three questions.
Yeah,
Second question is to sir. The question was, before path tracing using randomness, wasn't there any other method, deterministic method to do that?
No, it's very hard to generate these images with deterministic methods. Path tracing was the only one that was developed.
Okay. Thank you. Last question to you. Ma'am, you have worked in higher dimensions, right? So I want to know, how do you visualize them?
No, so I don't work in high dimension. This topic was suggested to me and I just gave a talk. And visualization
Any ways to visualize them?
Yeah, I mean, for 4D I tried doing that. I mean, there are multiple resources, right? If you look at a 3D ball, how would you explain it to someone in 2D? Like slice through it and it gives you disk, right? Similarly, if there is a 4D ball and it passes through your 3D space, what you are going to see is 3D balls that you see. Yeah. I mean, that is one method that mathematicians have thought of visualizing spheres in 4 dimension. And beyond that, it just fails. Yeah.
I have a question for Rachna. Over here. So, have you looked at any pyramidal shapes?
No. So I told you this is not my research area.
Okay.
Yeah, I just.
So just do you have any intuition, since you have done some work in this? So how would the volume of a regular pyramid inside a cube?
Sorry, I don't. I mean, I haven't looked at other shapes. Yeah.
Okay.
Testing.
Yeah. Welcome, everyone. It is my privilege to introduce a very old friend of mine, Sriram Krishnamurthy. We were classmates here in Bangalore, and he's moved on to become the professor of programming languages at Brown University. There are many other things I can tell you about him, but I think I'll let him speak for himself.
Oh, that was nice and short. Okay, well, thank you.
I can do interpretive dance.
That is the best introduction ever. Okay, good. Hello, everyone. My name is Sriram. Thank you, organizers, for having me on them. It's so kind of you to, I happen to be in town, and it's really gracious of you to have me here. So the topic of this workshop is about art and computing. I'm going to define art, in my case, very narrowly to be certain kinds of visual arts, and maybe even more narrowly once you see the work. But what I want to do is I want to talk about a very powerful connection between art and certain kinds of computing, but also talk about some of the limitations of some of the things we take for granted. Okay? Now, how many people here are computer science people? Computer science people. Wonderful. Okay, my family. Good. So, here is a thing that's going to happen to you over and over and over again. All right? So somebody's going to walk into your office and they're going to say, they say, well, I want to teach computer science and you're the expert. What should I do? Okay? This happens all over the place. If you work at a company, you work at a university, people come in and I'm getting a little feedback. Probably too close to the mics. Too close. Maybe. Okay. Still feedback. Feedback. Okay. All right, good. Thank you. Actually, do I need this mic? Why am I wearing a mic? I don't need a mic, right? No, they'll hear me in the back without a mic. Oh, YouTube. Okay, fine. Nobody is on YouTube anyway. Okay. They're probably watching like some rat video or something by now anyway. Okay, so people will walk into your office and they'll say, I want to teach computer science. What do I do? What are you going to tell them? Come on. You all raised your hands. Algorithms. Programming. What? Tell me more. What about programming? What should they do? Discrete math. Okay, what else? Huh? No, compilers. You're going to, okay, go on. Other answers. Computer networks. Other answers. Quantum computing. Other answers. Huh? Scratch, huh? Databases, Scratch. Go on. Fundamentals of the hardware. Yes. Huh? Yeah, automata theory. Good. Any other answers? Web development. Excellent. Theory of computation. Okay, good. So here's an exercise. Something similar happened on the Brown Computer Science Facebook forum, and somebody here said Scratch, right? So first answer is you should teach Scratch. Okay, and second answer is like logo. Maybe we should do turtles instead, right? And then of course there's always like that one person, right? So the one person who says, no, logo and turtles are all crap, okay? I gave up until I was able to learn C++. I would strongly recommend C++ as a first language for 5-year-olds or something like that, okay? That's fine. That's an opinion. Okay. Now, you've all told me you're computer scientists, right? Okay. So almost all of you are computer scientists, a few like respectable people in the room, but for the rest of us. Okay. So somebody walks into your office and they say, I want to make software. You're an expert. What should I do?
I would say narrow down the scope first.
Oh, you're going to ask them questions instead of giving them answers. Apparently, you're going to ask them what it is they're trying to achieve. Why? Why are you asking them questions? Yeah, go on. Huh? Serve better because software is complicated, right? Software has all these moving pieces. It's got all these characteristics and has all these consequences. So maybe we should understand the problem a little bit before we start proposing solutions, right? And what I ask you is, why is education any different? It's also a complex system. There are human factors, there are technical factors, right? There are lots of interlocking pieces, and if you screw it up, you will have massive consequences, okay? So education is just as hard a technical problem as building software is, but somehow we computer scientists like to start talking about solutions before we ask people about requirements and ask them about their problems. Okay? So hopefully you're all a little embarrassed now. Are you all a little embarrassed? Good. Okay. All right. So in general, anytime we try to do engineering, right, we don't start with solutions. We ask, like, what are the goals we're trying to achieve? And then we ask, what kinds of methods can we meaningfully apply? And then what kind of constraints are available? And we take all of those and funnel those through to describe any kind of solution tactic, right? Which is what you were suggesting I do in the software case. Okay? I'm going to ask you to think about doing the same thing when it comes to education as well, right? So what are the constraints that you face in schools? There's a lot of constraints, okay? So what age are the students, right? And you all started giving me answers without even asking what age the students were, right? Theory of computation, may be a great idea, may not be, depends on the age, okay? What prior exposure, right? Because all of your answers are predicated on what they already know, right? Is this a required class? Is this an optional class? How long is the class? How often does it meet? How often does it meet? Why am I asking, why does it matter how often it meets? How often it meets? Because? Do they need to attend it regularly? Recall, recall, recall. Ebbinghouse's forgetting curve. Within a week, they forget everything. So if they're meeting 3 times a week, that's completely different if they meet 1 time a week. Because if they meet 1 time a week, you're going to have to spend the first 15 minutes reminding them of all the stuff that they forgot last time. Of course, if you're a good educator, you're like, screw it, it's their fault if they don't remember anything. We'll just go ahead and teach, and who cares they learn anything, okay? But if you're like a crappy educator and you care about their learning and things like that, you might take things into account like cognitive factors like Ebbinghouse's effect, okay? Or things like how many students are in the classroom. A solution for 5 students looks very different from a solution for 50 students, okay? Is it even a class? Maybe it's like some after-school offering. Maybe it's not being offered during the regular school day, and that has all kinds of consequences as well, okay? Now, I think if I'd given you time, most of you would have come up with most of these characteristics, but there's many, many more things to think about as well. Do they have internet access, right? Do they have regular access to computers? Is the teacher new to programming or to computer science, right? Can the students type? Or do the students have any impairments? Like, are they, visually impaired? Some of you suggested Scratch. Everybody loves to suggest Scratch, right? CS for all says we shall use Scratch. Guess what Scratch does? Scratch asks you to move a little block into a tiny little target that's visible on the screen that lights up. If you have a motor impairment or if you have a visual impairment, how the heck are you supposed to drag something you can't see into a target you cannot match? But CS for all, apparently, okay? So we have to think about these kinds of issues, right? So this is why I like to say that designing a curriculum is also an engineering problem, and all of us are trained as scientists and engineers. If we approach curriculum design the same way we think about approaching technical problems, we will design much better curricula, okay? So that's my motivation. Hopefully I've embarrassed everybody, almost everybody in the room a little bit, so you're all a little awake now, right? Good. You've loaded up with coffee, loaded up with embarrassment, we're good to go. Okay, so now we get to important national issues like computing education, right? So every country these days has some sort of like national initiative. We want to teach computing for all, okay? All right, so here is our premise. R is this group that I represent called Bootstrap. Here is our premise, and depending on what I'm about to say will sound either obvious or shocking to you, okay? Which is, if you want to teach computer science, it doesn't mean you need to have a course called computer science. As I said, some of you will say, yeah, why not? Sure. But then I would ask you to think, well, then how else are you going to teach it? And if you're shocked, good. You should be shocked because it sounds like that's not how we teach anything else, okay? Back in 2009, my colleague Matthias and I wrote this CACM viewpoint, and we got like blasted for this. Like everyone's like, no, this is not the stuff we are allowed to say, right? This is forbidden. You can't say such things. Why do computer science doesn't matter? Oh my God, right? Okay, terrible. And what we said was, look, at the time, we predicted that in a few years, here's the problem, okay? you want to teach computer science, president has said, some president, prime minister, these people always say these things, right? Chief minister, governor, whatever, right? They say everyone shall learn computer science. They sign something with a big fancy pen, they have a big photo shoot, and then they walk away, right? And now everybody else is left trying to deal with the consequences of that decision, all right? Okay, we said, okay, great. How are you going to make room to teach computer science? Where is the room? Like, you all, I assume most of you, if you're at IISc now, you went to school at some point, right? You all went to school. Do you remember that time in the week where you had like an hour when nothing happened? There was no class, nothing? There was just a big empty hole in your calendar? Really? What was it called?
It wasn't called anything. It was just 3 hours.
It was just a free hour. Doing what? What did you do? Sorry? They call it zero period. Okay, so now can we take away zero period? Why is it there? It's there for a reason, right? So if we take it away, okay, fine. Here's what we're going to do. We're going to take away zero period and rename it computer science. We're going to teach you computer science then. Okay?
Computer science starts from 0?
Yeah, it starts from 0. Perfect. Yeah, starts from 0 period even, right? So even better. Thank you, Alas. Okay? Now, we predicted that in 5 years, people are going to say, we want to teach data science for all. Okay, now what are you going to do? What are you going to throw out? You've used up the 0 period, right? Should we throw out geography? We can make Indians as dumb as Americans. They don't know any geography. Okay? Should we throw out history? What should we throw out? Right? Math? Maybe we should throw out math. Maybe we can throw out computer science. Okay? And then we said, in 10 years from now, there'll be something else we can't predict. And sure enough, exactly 10 years later, people said we need to teach AI for all. So what? Do we throw out data science for all, which has already thrown out computer science? Where the heck do we make room for this? How do we do this? Right? It's easy for us sitting on the outside at universities to say everyone should learn X, but the schools have only so much room. They're already full. They've been full for 100 years. Okay? So there are space and time problems. So what we pointed out was, in general, just because you want to teach X doesn't mean you have to go create room for a course called X. We can think about other ways to do it. So what we said as Bootstrap, this is our group, what Bootstrap said is, we're going to teach computer science through integration into subjects that already exist in the school. Okay? If you can integrate into subjects that already exist, you already have teachers. Somebody's already paying their salary. By the way, it's not cheap to pay computer science teachers, because I hear there's some companies that hire people in computer science. I don't know, I've heard some rumors about this. And they apparently pay reasonably well too. So, okay, so there's already teachers. The subjects already exist. The teachers exist, right? But we have the dual problem of we now have to train them in computing. Okay? So we don't get ready-made computer science teachers, ready-made computer science slots, but we have to teach these other teachers how to teach computing. Okay? So our approach is basically, we have a bunch of curricula where we work with middle and high school, means roughly think like age 10, 11 onwards, okay? Beyond that. We're starting to work a little bit with slightly younger students, but imagine roughly like age 10, 11, okay? We assume they have no prior computing experience. In the Bootstrap algebra curriculum, they're going to build a video game. In the Bootstrap data science curriculum, they're going to build a data-driven report, okay? And they're going to do this by designing something of their own choice. I will talk about that. And then they're going to do it in about 20 to 30 hours, which is not a full semester, okay? Because if you try to walk into a school and say, we are going to replace your existing class, they'll be like, no, we're quite happy with our existing class. Thank you very much, right? So you have to find a way to inject into existing classes, and you can't do it by an aggressive takeover method, okay? And they're going to learn both computing and either algebra or statistics or whatever their home discipline is. And we've got, similarly, a curriculum for physics and some other things as well, okay? And we've got all sorts of like nice demographic numbers, whatever. But the key thing I want you to note is in our very logo, we say we care about 3 goals. Equity, which means we want to deal with the concerns of all students. Scale, which is, it's very easy to be equitable in a very small setting. You want to achieve this across the country or across countries, okay? And you can do both of those if you don't care about rigor, okay? But we also want something rigorous. So this is like a pick one or maybe a pick two situation, and we want to pick all 3. I'm not going to say we succeed yet, but that is our goal. We want to set the hard task and try our best to solve it, okay? So the rest of this talk, I'm going to focus on one of those curricula, because that's the curriculum that ties to the theme of the workshop, which is art and computing. Okay? So bootstrap algebra. Remember what I said bootstrap algebra students do? Quick quiz. What did the bootstrap algebra students do? They built a video game. So you can already see where this is going, right? Okay, so we're going to talk about a video game. All right, so back to this picture, right? So we are going to use visual media and computing. That's the point of today's talk. Okay, we're going to teach them just as much computing as they need to achieve this. This is not like a full-fledged introduction to computer science, because remember, it's being taught by like a math teacher who's not a computer scientist, which is very relevant to what we're doing. Okay, and of course, what are the goals we want? You know, in addition to things I talked about, we want like engagement, retention, and so on. But we also have a very specific curricular goal. Okay, our very specific curricular goal is functions. Functions in mathematics. Now, why do you think I'm picking functions in mathematics as such an important focus? So to explain that, I'm going to do a little bit of a quiz here, okay? I'm going to call out something, and you're going to respond, okay? Everyone awake? Everyone awake? Like, did you have like a lot of sugar in your coffee and you're starting to like go to sleep? No, you're all still awake? Okay, good. 5 plus 3. 14 divided by 4. Too much sugar? 14 divided by 4. 5 plus 3, the whole divided by 2. X plus 3 equals 14. F of x equals x squared. Dead silence. What happened? Yeah, what was that? What's the question? Oh, wait a minute. Until now, I never asked you any questions. I did not ask you a question. I said 4 plus 3. I said x plus 3 is equal to 14 or something. I never asked a question. Okay? Because you are all carefully programmed machines for answering these questions. And how do you answer them? You have an algorithm in your head, and it's like a Pavlovian response, right? The moment I say this, boom, the algorithm kicks in and you start giving me the answer, right? And you're all like IISc people, so of course you're the best people at solving these algorithms. That's how you got here in the first place, okay? And then you get, and this is a problem with mathematics education. Up to the point of functions, math education is basically a algorithmic process. They teach you algorithms, okay? First, they give you an algorithm where they teach you, like, you know, addition, 2 times 3, 3 times 4, and they make you say it over and over till you remember. Then they give you a multiplication table, right? That's also an algorithm, right? You have to know how to look up things in the table. You have to memorize the table. It's a finite function. You memorize it, right? Then they teach you, oh, I don't know, like long addition, right? And you have to carry things this way, carry things that way, whatnot, okay? Then they teach you long division. You have to learn about borrowing, right? Which is a whole nother thing, right? It's like early introduction to Rust or something. So you have to learn how to borrow, right? So they teach you all these complicated algorithms. They say, oh, draw it like this. So you have to draw this like this and that like that. And sometimes students get confused. They look at a square root and think it's division. And it's like, no, 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 you can't do that, etc., right? And then you get to functions. Functions are abstract objects. On their own, there is no algorithm. When I say f of x equals x squared, you suddenly said, what's the question? Because it's an abstract object. It just sits there, doesn't do anything. If I said f of x equals x squared, f of 3, your algorithm would kick in again. But I didn't give you that chance, right? So it's an abstract object. It is the first time in mathematics, I mean, in some sense, all of mathematics is abstraction, right? What the hell is 3? 3 is one of the ultimate abstractions, one of the great abstractions that people discovered, right? Before that, you probably had like a farmer who had to count like bales of hay, and another farmer had to count cows, and there was some sense of like, it kind of feels like the same sort of thing, you know, like a bijection, but they didn't have a name for it, and then somebody said, we shall come up with the name 3 or teen or whatever you want to pick. Trois, whatever, right? Pick your language, right? They picked this abstraction. So in some sense, it's always been abstract, right? But we turn it all into concrete algorithmic activities, and now you finally deal with abstraction, naked abstraction. What's even worse is we are going to ask you things like, is this function injective? Well, wait a minute. That is an abstract question about an abstract object. It's not surprising that math starts to become difficult, okay? And students also react in different ways. There's a really good body of literature about this in math education, where students start to say things like, they go from saying math is hard to I can't do math. You notice the difference? First is a global statement. It's a shared emotional suffering, if you will. The second is a personal thing. I can't do this, right? It's also, this also comes into schools around the time where other things are happening, you know, like hormonal changes, et cetera, social changes are happening. So all of this is complicated, right? Schools are a socio-technical system, and so you have to take all of these things into account. So all of a sudden, math starts to become difficult, or maths, I'm sorry, I know I'm in India. I've been in the US too long. Maths, every time I say math, you can stick an S at the end of it, okay? So math starts to become difficult, okay? So that's why we focus on functions. And what does it mean to teach somebody functions? I'm going to argue that there's two fundamental skills. One is function composition, the other is function definition, okay? So I'm going to start by talking about function composition. So we invent a new notation. I'm not going to go into a lot of detail, but did you, when you were in school, probably in English class, do you remember like they would draw these trees, they'd say like verb, noun phrase, verb phrase, things like that, like sentence structure, things like that. They call diagramming in some places, right? Parts of speech, okay? And you probably like went to, if you were like me in English class, you're like, yeah, whatever, right? Okay, but then you go talk to math teachers about like BODMAS or PEDMAS or whatever, right? And about like rules of operator precedence, and they're obsessed with this problem. And in fact, the easiest way to create a flame war on Twitter is to post something ambiguous and ask, what is the answer to this math expression? Oh my God, math teachers are sweet, caring people, and they will call you an asshole for having the wrong answer. Like, do you know any mathematics at all, you idiot? Like, totally, it's amazing, it's hilarious, and every 3 months this happens, okay? Because they don't have a notation for diagramming the expressions. They're trying to understand the grammatical structure. So we create and teach this diagrammatic notation. I'm not going to go into it here, but the point is this is one of the things that we do. But the other thing we do, and you're like, is he ever going to talk about computing? I told you computing doesn't matter, so maybe not. But yes, I will. Okay? We also teach them to do some amount of programming. All right? So how about we write some code? All right? So let's do this. Okay, so I have here a programming environment. I've got like, anyone know what that is an icon of? Yeah, exactly, good, okay. You do know cricket, right? I mean, people are a little quiet here. You recognize this as cricket? Okay, all right, so let's say we want to recreate this image, okay? So what are we going to do? We are going to do decomposition followed by composition. Decomposition, let's break a bat down. What are the parts of a bat? Handle and? Yeah, like a blade. Yeah, exactly. Handle and blade. Okay. So what does a blade look like approximately? Let's not get over. I understand there's always some purist here who's like, I got to get the angles exactly right. What's a blade? It's a rectangle. Great. So how about we say, I don't know, 20 by 50. It's solid and maybe like tan colored. Okay. Right. Okay. What about the that's a reasonable approximation, right? Okay. So let's call that the blade. Okay, and now let's create the handle. What's the handle in this case? So, yeah, it's another rectangle, right? So rectangle, let's call it, I don't know, 20 by 10, solid black, okay? You like that? No, why not? You want 10 by 20? Sure, not a problem. This is programming, we can change these things, okay? All right? Okay, so what's this now? This is a handle. Okay. Now, how do I get a bat out of this? I have to combine. How? Add them both. Add. Can you add? You can add numbers. Can you add images? No, you have an intuition of some kind of add, right? What kind of add do we want to do? Join, union, you all like too much, you people know too much math, union sets, right? How do you want to put them together? How does the bat handle combine with the blade? One goes on top of the other, thank you. Okay, so let's try saying on top of handle, comma blade, okay? And I will get an error saying I don't know what on top of is, okay? But if I say above, aha, okay? All right, so what's this now? What? Ex-Microsoft person, I'm looking at you. Okay, yeah, okay? Okay, so now is that the bat we have in that picture? What was that? Rotate. So rotate bat by what? 45 degrees, okay. Okay, what's going on? Can you figure out? Too smart. What's the error message say? Okay, all right. You got to read the error message, it turns out. Okay, what's a ball? Circle. So ball, I'll just call this RB, okay? And so ball is a circle, what? Five? Like that? Yeah, good. Everyone happy with that? Okay, now what do we do? Combine, how? Next to? Yeah, below. Let's try this. Overlay ball. How about we overlay bat ball? Okay? RB? So you want to do this instead? Okay? Okay. Now, well, it's not exactly. Okay. So, what is going on here? We are using visual composition. We're doing function composition here. We're composing functions. Okay? And we're using visual composition. Now, I acknowledge this is a very boring way of teaching composition, right? What you normally do in school, you say f of x is equal to x squared plus 3. G of y is, y cubed plus 4. What is f of g of 14? Right? Okay, I claim the answer is 247. Am I right? Do you care? Okay, you all cared awful lot, right, when the ball wasn't visible. Okay? So all of a sudden, taking the exact same concepts and translating them into this visual programming domain, and all of a sudden people start to care. Okay? So here is the project that we make students do. You're going to design a logo, and you're going to create the logo. And you create the logo using only function composition. Right? And again, when you pick the logo, you're going to be pretty unhappy if parts of the logo are not visible, if the parts of the logo are not there. But you also learn functions like above and overlay, not just f of x is equal to x squared. Right? And you learn that there's a rich body of functions that operate on a rich body of types, including images. You can have functions on images, and you can program with them. Okay? So here is an example of one of the logos that one of our students made. And this is not a student who, as far as I know, ever identifies as being a mathematician or anything like that, right? This student would never have written function composition this deeply nested over numbers, because why the heck would you care? Okay? But they wanted that logo. And all of a sudden they care. Okay? Good. So this is the first part, which is this is how we're going to get students into function composition. All right? Now for the more complicated part, which is function definition. Ready? So there's going to be more homework for all of you. Ready? 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 Okay. Pradeep, you can read email later. So, he's tweeting probably. Okay. So here's what we're going to do. I'm going to use an activity, a really cool activity that comes out of math education. And if you're an educator, I strongly recommend you try this out. Okay? So the idea is, it's called notice and wonder, which is I give you an object of some sort and just ask you what you notice. All right? And this is a great thing to do in classes, because even a student who does not identify with the subject is like, there's always like, there's always like, some hacksaw in the class who's like, I know more about, like, I have like Arch Linux, therefore, I'm like the cool kid or something like that. But even the person, and the Arch Linux people are a little embarrassed now, right? But even the person who doesn't identify, he's like checking his Arch Linux version, right? And even the person who doesn't identify with it will be able to notice things every bit as well. So it gets more students participating and feeling like they belong in a class. What do you wonder is then hypothesis generation. I'm not going to do the wonder part, but I'm going to do the what do you notice part. So I'm going to, it's a little hard to read. I'm going to show you a game, okay? I'm going to ask you about what are the things in the game and what changes about them. All right? And our job is to fill up this worksheet. You good? Ready? Okay. So here is the game. Okay. All right. So remember, our goal is to fill out, our goal is to fill up this worksheet. Okay. So what did you notice? Yell out things that you noticed. Go. Huh? Mario. What was it? Ninja. Other things. Dog. That's actually a cat. The game is called Ninja Cat for a reason. Okay. Cat. Clouds. And then we saw gemstone. It was like a ruby or something like that, right? What else do you see? Sun. Yeah. Huh? Score. So you're proving that you weren't like reading email. Okay, good. What else? Anything else you notice? Jumping. Okay, what else? A moving cat. Okay, so how were these things moving? What changed about them? What changed about the cat? Position in x-axis. What changed about the ruby? Position in x-axis. What changed about the cat? X, Y. Okay, so the point is we're going to fill in this worksheet something like this. Okay? What do you notice? You're going to fill in the worksheet talking about what you noticed, and you're going to describe the actions. Okay. So far, so good. No computers involved, right? Okay. Now we have to actually program a game like this. Okay. Let's just say for now, we want to program Ninja Cat. Okay. We'll get to the part of like maybe you don't want to program. Do you all want to program Ninja Cat? Yeah. You do? Oh. Okay. You're a very gentle audience. Okay. All right. So here's what we're going to do, right? It's important for us to understand that there is no such thing as a movie. You ever been to a movie? You've been to a movie? Well, you couldn't have been to a movie because there's no such thing as a movie, and some of you just agreed with me. Why were they called movies? Because they move. Do they move? No, they do not. That's the key. In fact, they were called movies as a marketing strategy because there is no movement, right? All there is discrete frames, and people discovered that if you show discrete frames about 24 times a second, your brain will play this great trick on you of making you think there is motion. Okay? So even the coolest game in the world, the coolest movie in the world is just a sequence of still images and motion, and we can exploit that fact as well. Because, remember, our goal here is we're trying to use art to teach computing and math. Okay? So, step one here is we're going to identify the core information in every scene. Okay? If you're a software engineer, you can call this a model if you'd like. Okay? Right. So there's some position, player is in some position, danger in some position, blah, blah, blah. Okay? And now the step two is we have to perform the updates. Right? And now this is where computer scientists are a really bad person to talk to. Okay? Because they will screw this up. Right? Because your typical computer scientist will be, well, you know, you undraw the previous image, you move all the variables, and you draw a new image. Okay? Okay, that's fine, but that does not map to mathematics in the slightest. Okay? So instead what we're going to do is we're just going to construct functions that, given a current state, compute a new state. Because our goal is to teach functions. Our goal is not to teach imperative programming. Our goal is to teach functions. Okay? And similarly, going from this image, from this information to the picture is just a drawing. We already saw how to do this, right? Do you think I could turn this into something that's parameterized over the sizes? Wouldn't be too hard, right? I just have to change that. So we know how to write functions that consume information and produce images. We can also write functions that consume information and produce new information, right? So these are both functions. And we are trying to teach you to define functions, right? So for example, an update function might look like this. What is the new position of the danger, in this case like the cat, right? It does look a bit dog-like, doesn't it? A little dubious about calling this ninja cat. Anyway, okay, I'll discuss this. Okay, so that might be one way you do it, right? It's moving in the x-axis in the negative direction, okay? Or what do you do about the player? Well, the player is going to move in the y direction, up or down, based on a keystroke, right? And similarly, the draw function is you take this, remember overlay? Anyone remember overlay? Okay, we're going to use overlay. We're going to use the functions that we just used. So all of the things that you learned for drawing a logo are now useful for generating the scenes, right? And you put these together and you get a game. And we do this, okay? So in fact, what we do is we take the mathematical learning objectives and turn them into a series of frustrations with the game, okay? You start by building a very basic game, and then you say, well, wouldn't you like to know when you get to the end? Yeah, I really would. My game sucks. Okay, good. So to do that, I'm going to have to teach you about something in programming called Boolean expressions, right? And to do that, I have to show you comparison expressions in mathematics. Wouldn't you like the game player to come back around? Yes, I would. Okay, well, because that's what games do, right? Players scroll back around. How are you going to do that? I need to teach you about something called the mod operator in programming, and I need to teach you about modular arithmetic in mathematics, right? Wouldn't you like it if you could respond to keystrokes? Yes, I would. Okay, so I'm going to have to teach you about conned expressions in programming, but that corresponds to piecewise operations in mathematics. Okay, wouldn't you like it? Wouldn't you like to be able to detect collision? Well, of course, like, oh, what's a game without collisions, right? Okay, so I'm going to teach you some programming for it, but I have to teach you about the Pythagorean theorem in mathematics. So the point is, everything here is a frustration, a game challenge. Every game challenge turns into a programming activity, and it turns into math content as well. And all of these are very tightly aligned. And when you're done with all of that, not only do you have a working game, because you have a game, you got to have a launch party, right? So you have a launch party. So we make students work through these worksheets, right? So they have to write. They don't just get to write code. They work in a disciplined way. They write a contract and purpose statement. So basically, they write type declarations, okay? Then they have to write concrete examples. In computer science, we call these test cases, okay? And then they finally get to abstract over the test cases and write what you finally might call code. Now, the key thing is, these are multiple different representations of the program. All of these map to mathematics. The type is the domain and the range. The examples are the tables, and the code is the symbolic form. And a thing in the math literature that teachers struggle with, is a well-documented struggle, is to explain to students that these three different representations that are visually completely different, they look completely different, are all closely interrelated because they are all talking about the same thing, right? But it's obvious they're talking about the same thing because they're all trying to help you build your function, right? So for each function, you go through this worksheet and you understand how to do this, right? So the research side of this is studying a question called transfer, which is if you think you've learned something in one domain, can you translate it over to the other domain, okay? So we spent a lot of time thinking about the transfer, and this research is important because I want to remind you of my talk title, which is, it's all fun and games until you can't pass the math class, right? Ultimate goal is to improve the math class. The ultimate goal is to improve math education. Programming is a tool for that, and the visual arts are a tool to enable the programming, but you're doing all of this to improve the math. So if you don't study the math, you haven't achieved anything at all. In fact, you've done two things. You've maybe hurt their math education, but the other thing is you have lost credibility with the math teachers you're trying to convince to use your curriculum, right? So when we go to a teacher and talk to them, they want to know, how do I know this is actually going to help my students learn more math, right? No amount of wonderful entertaining that I do is going to convince them of that. You have to have solid research backing. Okay? And of course, I also want to give you my favorite quote. This is from the director of the STEM Center at University of Texas at Austin. It's a very Texan quote. Carol's a wonderful person, but it's just such a great quote. Okay? So that's what we do. Okay. Now, I want to talk about 3 things related to this curriculum. How am I doing on time? Yeah, okay, I've got 14 minutes, right? 14 to 15 minutes roughly. Okay, good. So first thing is, I want to talk about degrees of freedom. So we talked about Ninja Cat and whether Ninja Cat is a satisfying game, okay? We don't actually make our students program Ninja Cat. What we do instead is we give them a worksheet and we give them 4 degrees of freedom, okay? They get to pick, where does the game take place, what is the player, what is the target, and what is the danger. You remember for Ninja Cat, where did the game take place? In some external setting, some land kind of thing. What was the player? Ninja, yeah, Ninja Cat, right? And then, sorry. And what was the target? Ruby, and what was the danger? The dog, cat, something, whatever animal that was. Okay? All right. So those are the parameters. So here's an example of a student response, right? My game takes place at the beach. The player is a mermaid dog, maybe like a mer dog, which can fly. The target is a fish-shaped dog treat, okay? Because it's a mer dog, remember? And the danger is a great white shark, which can also fly, okay? So this is a student having fun, right? And here's some examples of pictures that students make, okay? They look even, yeah. Will you recognize that? Yeah, okay. So do these look even remotely similar? Not even, I don't think there's even like colors in common. These students are all going to build the same game. The games are fundamentally isomorphic. They are isomorphic to the Ninja Cat game. Why is that important? Because if you let a student build whatever game they want, they will compromise on the math or programming. They're like, oh, collisions, how do I detect collisions? Well, I need to teach you a new piece of mathematics called the Pythagorean theorem. They're like, I don't care about collisions, it's fine, it's okay. We'll just bump up the score at random, right? That doesn't work if the goal is to teach mathematics, right? Also, if the student's allowed to create any darn thing they want, remember, we're not working with CS teachers, we're working with math teachers, statistics teachers, in some cases in the data science curriculum with like history teachers, right? They're not experts, they're not going to be able to debug a class of 30 students, each doing a completely random different thing, okay? So, students do this, and one of the things we wanted to study was, how do students feel about the games that they've created, right? So there are 3 fundamental questions I want to focus on. One is, did you feel like you made a real game? Green is strong agreement, blue is agreement, right? And yellow and red are bad, right? Green and blue are good. And you can see about 75% of them basically are in the good category, right? The other 25% basically are gamers, by the way. Right? No, I'm not, but seriously, they're like, this is not a real game, right? World of Warcraft's a real game, not this nonsense, okay? But is your game different from the game the others made? Even the gamers don't detect it, right? Most of them think they've actually made a different game. And the most important question is, are you proud of the game you made? And most of them feel a sense of pride. They made something, right? That's the thing that drives them, it motivates them, it excites them. So we're using art to excite and motivate the students so that they learn mathematics and stay in touch with critical math functions that they need for mastering STEM disciplines down the road if they want to. Okay? And here's some quotes, right? Why do you build your game? Slots are cute. Zombie marshmallows are very necessary. We thought it's funny. We like dogs. But then they get some more serious. I wanted to point out something about animal endangerment, or I was passionate about the environment, or it's a story, or I did it because my sister loves Batman. I want to make a game for her, right? So you can start to see there's actually very serious themes behind these games, right? They are storytelling. They're telling things about things that matter to them. Without a whole lot of flexibility, they can express themselves very richly, right? This is one of my favorites. You know what's going on here? Yeah, I think some of you are starting to figure it out, right? So basically, this was a student who read about how we're blowing up satellites in space, right? And we're polluting space. And she wanted to raise awareness of space junk. So you have space junk, right? You have junk. This butterfly net is supposed to catch the space junk, and the asteroid is the thing that's going to destroy the butterfly net, right? There's actually a very profound storytelling going on in this scene that it didn't take a whole lot of flexibility while the student was also learning math, right? So one question you might have is, well, you've got 4 parameters. Why don't you have a 5th, right? Wouldn't that be better? Because you can express even more things with more parameters, right? Here's a fun thing. We used to have a 5th parameter. We had a parameter of like a thing that moved around on the screen. And you know what happened when we had that parameter? Everybody made a shoot 'em up game. Everybody is making shoot 'em up games. They're like, this sucks. What can we do? Well, we got rid of the projectile, and then the storytelling got better. So more parameters isn't necessarily better. And I'm bringing this up because I think in computer science, we have a fetish about this sort of thing, right? We think, computer science teachers think that if you put the slightest constraint on students, you've taken away like their fundamental rights, their fundamental freedoms, right? It's like enshrined in the Constitution. Thou shalt not tell computer science students anything about what they can't do, right? But in reality, I think it's very different. First of all, if we give unfettered creativity, we can't get learning objectives. You can't have both. If you need a learning objective, you can't then do any damn thing you want, right? Any Scratch fans in the room, I hope you're paying attention, all right? Secondly, every creative artist thrives on constraints. Now, I'm not the most qualified person to say this. We have actual artists in the room today, and they can confirm or deny. But if you read like literary masters, which I have read a lot about, they thrive on constraints, okay? And finally, I'm beginning to think like maybe this whole creativity thing is a little overrated, right? Because people keep saying these things, we keep designing these curricula in computer science, and then the learning objectives always go out of the window, okay? How am I doing on time? I'm going to skip this part. It's kind of like fun math stuff, but I'm just going to skip this, and we can talk about it later. I want to talk a little bit about accessibility, okay? Because there's a lot of arts, but as I said, I'm focusing on visual arts. And visual arts are a problem for people who are visually impaired, right? And if we want to build computing for all curricula, we have to think about these issues. So we've spent several years working on this. We've worked on the process of writing code. We've worked on IDE navigation. You know, you saw my interactions window, a read-eval print loop. It turns out the visually impaired community has spent a lot of time thinking about conversational modes for chat, right? So we take the metaphors that they use and borrow those and use them. When we construct images, we maintain the scene graphs, and so we can verbalize the scene graphs. And finally, there's a whole bunch of work in the visually impaired community about what is called semantic prioritization, which is how you read things out. Because if you've ever worked with somebody visually impaired, they get audio at about 3x the speed that we do. Okay? And so there's whole techniques they have figured out about how to present verbal, textual, and audio cues to listeners so that they can take advantage of that speed and not get confused. Okay? So we do all of these things. And again, Scratch people, stuff for you to think about. Right? If we want computing to work for everyone, we have to think about these issues. Our proudest moment was we actually got a school for blind children in Alabama to use the Bootstrap curriculum. Right? And the kids were super excited because they said usually we get the curriculum for blind kids, and it was super exciting to get the same curriculum that the regular schools are using. Right? There's a lot of ways to go. I'm not claiming by any means we've solved it, but I'm saying we all need to think about this. I want to raise awareness. Okay? So that's the end of my talk because I want to have time for discussion. So a few final comments. First of all, we can integrate. We can do computing through integration. In fact, I'm going to make a stronger, bolder statement. I think computer science should not make the mistake that mathematics made. Oh ho. What mistake did mathematics make? We claim that math is foundational because it speaks to every other discipline, certainly every discipline in STEM. So what do? Instead of teaching math in context, we put mathematics in a silo, remove it of all context, right? And we say, oh, this has some applications to such, and then move on to teaching math as its own inert discipline. And guess what? Students don't see how to transfer ideas from math to those subjects or from those subjects to math. So I'm going to argue that integrating computing may actually be a really good idea, because if we claim computing is like the new math, right, the new foundational subject that everybody should learn, they should learn it in context. After they've seen it in 3 different contexts, then it makes sense to present it as a subject in its own right. Okay? But it's got lots of pitfalls. It's not easy. There's tricky stuff. Happy to talk more about that. It's not enough just to have pretty material. You've got to do much more. There's whole curricula. There's, et cetera, et cetera. It's essential for us to understand the constraints of humans and systems, going back to what I started the talk with, right? And finally, it's very important in these integrated settings, you've got to let the host discipline be the top-level driver, right? Computing, again, has this very arrogant attitude of going into other subjects and saying, let me tell you how to teach your subject. You can tell them, right? But if your goal is for them to listen, not so easy, right? So that's kind of what's been our secret to success, is we work with people in other disciplines, learn the methods of those disciplines, and then figure out how to create a curriculum that integrates. All right? So last slide, I showed you this picture. If all you take away from this talk is this picture, when somebody comes and talks to you about curriculum, that alone will be a success as far as I'm concerned. And here's my contact information if you need to reach me. And now, I am ready for your questions, your comments, your criticisms, your complaints, and everything else. Go for it. And if you can use a mic, that would be even better. Right there. There's another one. There's another hand over here and another hand over here.
Am I starting? Okay.
Yes.
Yes. So what are the challenges that the teachers typically face right now?
Yeah, so for us, because we work with teachers in other subjects, the challenge is getting comfortable with computing.
Right? Even for the maths, I want to know.
Oh yeah.
What are the most common challenges?
Programming is just hard, right? We don't like to talk about this. I don't want to step on this. Okay, we don't like to admit this in computer science, but programming is actually hard. It's an acquired skill. And the key thing is, look, have you had a class of 30 students have bugs and try to help them all at the same time? Okay, imagine now trying to do that with no computer science training. Okay, that is the problem we confront. In fact, the reason we use things like worksheets is to give a structured approach so that the teacher can say, which step are you stuck on? I expected to see this at this step, I expect to see, and if the student says, I skipped those steps, it's like, go back. Do the steps again, right? In fact, we find that often math teachers do a lot better with our curriculum than CS teachers. Why? Because CS teachers like worksheets. Worksheets are like 19th century or some primitive technology. Who the hell needs worksheets? They're going to sit in front of the terminals and code. And guess what students do if you stick them in front of a terminal? They make a mess. Okay? And the worksheet saves that mess. Math teachers are perfectly comfortable with worksheets. The students usually have a more pleasant experience. So the computing part is a non-trivial challenge. Just because you're a math teacher does not make computing easy. Even the computing teachers struggle a little bit with computing, but the math teachers certainly do.
Okay. And one more question, how much training do you have to give to the math teachers?
That's a great question. We started by doing week-long trainings in the summer. We found that was too much, that was an overload. What we now do is we do some amount of training in the summer, followed by continuous training during the school year. We've done actually 3 different models. We don't have a perfect model because at least the summer you can get their attention, okay? During the school year, it's hard to get their attention. But if you overload them in the summer, then they're like, this is such a hard curriculum, I'm not going to teach it, right? So we've been looking at sort of spiral models instead, where you teach them a little bit in the first year, more in the second year, more in the third year. We've tried a few different models. We have a whole paper describing these models. Mostly it's like we don't have a great model yet. We're working with tough constraints. So I wish I had a good answer for you. All I can say is all of your instincts are correct on this. It's hard.
Thanks.
Yeah.
Yeah, here.
Yeah, no, I know you're here. I'm just looking for other hands. Yeah.
Yeah, so it's coming back to Scratch.
Yeah.
And it seems to be the darling of everyone.
Yeah, sure.
But I got as a working programmer, I felt some fundamental conceptual issues.
Okay.
Like in terms of the functions that you define in Scratch, they can't report or return values.
That's right.
And I've seen that
they're not functions. We broke functions. Congratulations.
And I see that becoming like an impediment for actually getting into the weeds of computational thinking, right? And in India, we had this pandemic of EdTech, coding for kids kind of a platform.
Right.
Every one
I
of them.
follow the IPL, so I saw all those ads in the US as well. So,
every one of them picked Scratch as a platform, right? Like, do you have any thoughts on how to overcome that?
No, so the way I look at it is if the competition wants to do stupid things, that's great for me. Yeah, I mean, the point is what? You're not going to go to White Hat Junior and tell them what to do. They're going to do what they're going to do, right? So I would say, think about these issues and then make smarter choices than them. And hopefully over time, those smart choices will win. I don't know. Other questions, comments, thoughts, criticisms? Come on, yes. Hold, quick. Other hands, if you have questions, raise your hand so we can get the mic to you. Somebody has a hand up there? Yes, fantastic. Here first.
Hello, sir.
Hello.
I don't have any questions, sir, but I would like to become a professor in teaching field. I really like your how the way you're teaching. Really, it's really impressed me a lot.
Well, I appreciate it.
I like to become like you, sir, like you in teaching.
No. You should do a lot better than that. Don't do that. That would be a mistake. But no, I appreciate it.
I love to teach, sir. Actually, when I'm really exciting when I teach to. Right now I'm a postgraduate student in CSC. In my college, I used to teach in lab sessions or I take seminars a little bit. I love to teach when I'm teaching, sir.
That's fantastic, and we need more teachers. That's great. And I bet when you go out for lunch or whatever, there's a whole bunch of people in this room who think like you, and you should all talk to each other and find ways to get more practice teaching. Good. Thank you. Yes?
Have you tried implementing any version of this here in India?
Well, so we do. I mean, we don't implement very much in the sense that we work with people who want to reach out to us. So I know we have a handful of users, but I don't know. We don't. One of the things is many of us who built this project are very. We used to do security and privacy research, so we're very conscious of those issues, and so we don't do a lot of deep tracking and stuff. We don't do I don't know what White Hat Junior probably. I should probably say that. I don't know what they do, but we don't do that. So we don't know a whole lot, but we'd love to work with partners in India. Happy to share all the lessons we've learned. All of our materials are free. Every single thing is free. This is a deep principle for me. All of my textbooks are free, software is free, Bootstrap materials are free, everything is free. So anybody who wants to pick it up, we do not want cost to be a barrier, right? We don't have Indian languages. We have some Spanish versions of material because that matters in the US and in South America and so on. We don't have Indian language versions, but again, we'd love to work with people. Okay, cool.
So we have time for just one more question.
Last one, make it good, go.
Sir, I have a question. Now this question is with respect to the student.
Yes.
Okay, the student is already, I'm speaking with respect to India.
Yeah.
I won't speak with respect to America, I'm not aware about it.
Sure.
So with respect to India, student is already overloaded by at least 6 subjects.
Yes.
With addition to this subject, what do you think? Wouldn't the
But
student...
I'm not adding, right? I'm just teaching their existing math in a different way. I'm not adding a new subject.
You already added one more thing, that the time limit. There are a lot of things in the syllabus. Will you be able to...
Great question, very good question. Here's what we do. We take our materials take, let's say, 30 hours, 25 hours, okay, the Bootstrap algebra material. It takes about 20 hours to cover the same material in existing math classes. So we're not adding 25 new hours, we're adding about 5 new hours the first time the teacher teaches it. As they get more familiar, they speed up, and it's a very small delta. If you are absolutely right. If you walk into a school and say, I want 25 new hours in your curriculum, they're like, I do not have it. Just like they don't have a course available. They don't have anything available. The curriculum is packed. It totally is. I know because I went through that system. It's completely packed. It's packed everywhere, okay? The key thing is to teach the same materials in new ways as opposed to teaching whole new materials, right? Our data science curriculum, same way. We work with history teachers. We say, we're going to continue to teach history, but we're going to do it in a new way. We're going to teach stats in a new way. We're going to teach civics in a new way, right? Rather than throw anything out, rather than make whole new room, we're changing the way we think about teaching it. That's the key.
Thank you, sir.
Thank you.
Okay.
All right, thank you all. Oh, is this when we do the thing? We do the thing. Come, let's stand here so somebody can, who else is going to get a photograph? Oh, thanks. Thanks. Excellent.
So those of you who don't know, Sridham is also probably the most popular computer scientist in social media. And if you like his talk or this program, just share on social media. You can tag CSA, IISc, etc. And there's a QR code, something interesting is there. You should just scan the QR code and find out what is there and then fill it up. Okay. Thank you. So the lunch will be served now. It's till 3:30 again we come back. No, 2:30. We come back for the session on comics drawing.